Hello there, and welcome to Science for Sleep, where curiosity gets comfortable, difficult questions are allowed to slow down, and science takes its time explaining the things that refuse to be simple. Tonight, we are looking at a claim that sounds as though it belongs in a science fiction film but begins with something far less dramatic. Old photographs of the night sky. Not digital images, not satellite recordings, not radar tracks from a military station. These were glass photographic plates exposed through a telescope at Palomar Observatory in California during the years between 1949 and 1957. Astronomers used them to record stars, galaxies, and other distant objects. The process was slow, physical, and sometimes imperfect. Light passed through the telescope, reached a chemical coating on a glass plate, and left behind a record that could be studied long after the telescope had moved on to another part of the sky. Decades later, researchers looking through those records found something unexpected. Across the plates were brief points of light that appeared in one image and then vanished from later images. Some were isolated, others appeared in groups. A few looked, at least at first glance, less like stars and more like flashes produced by sunlight reflecting from objects much closer to Earth. That would already be interesting. It becomes more interesting when we consider the dates. Many of these lights appeared before October 1957, when the Soviet Union launched Sputnik 1, the first widely recognized artificial satellite to orbit Earth. Before Sputnik, there should not have been ordinary human-made satellites passing overhead. There were no crowded orbital highways, no communication constellations, no weather satellites, no discarded rocket stages, and no steady stream of metal debris circling the planet. The space above Earth was not completely empty, of course. Meteors crossed the atmosphere. High-altitude balloons drifted through the sky. Aircraft flew below. Natural objects moved through the solar system. Cameras produced defects. Dust settled on plates, emulsions cracked. Tiny flaws could become bright spots that looked more meaningful than they were. Even so, the timing created an uncomfortable question. If some of those points of light were genuine reflections from objects near Earth, what exactly was reflecting the sunlight? That question is at the centre of tonight's investigation. The work is associated with astronomer Beatriz Villarroel and the VASCO project, a research effort that searches old images of the sky for objects that appear, disappear, or change in ways that deserve a closer look. VASCO stands for Vanishing and Appearing Sources During a Century of Observations. It is a name that sounds slightly mysterious, although the method behind it is practical. Researchers compare older astronomical photographs with modern sky surveys. They ask whether a source seen in the past is still visible today. If it is gone, they try to understand why. Usually there are ordinary explanations. A variable star may dim, a supernova may fade, an asteroid may move between exposures, a plate may contain a flaw, a modern image may simply fail to capture an extremely faint source. Occasionally, however, the explanation is not obvious. In one part of this research, Villarroel and her colleagues examined short-lived sources recorded on plates from the years before the first artificial satellite entered orbit. They argued that a group of 349 transients showed patterns that might be consistent with brief reflections of sunlight from objects closer to Earth than the stars behind them. That does not mean the researchers proved that the objects were alien spacecraft. It does not mean scientists have discovered a forgotten fleet parked above the planet. It does not mean every unexplained dot on an old photograph represents a machine, a visitor, or a civilization watching from a polite distance. The claim is narrower than the headlines often make it sound. The researchers identified statistical patterns that they believe are difficult to explain using simple plate defects alone. Other scientists disagree. Critics have suggested that the results may be caused by flaws in the photographic material, incomplete filtering, telescope scheduling, balloon activity, solar conditions, biased comparisons, or statistical methods that make weak patterns appear stronger than they really are. This leaves us in a familiar scientific position. There is an observation, there is an interpretation, there are objections, there is not yet a final answer. for a sleep science video that may be rather convenient. Nothing encourages the mind to settle down quite like a mystery that has survived several decades, thousands of photographic plates, and a considerable amount of professional disagreement. Before we continue, I would like to know where you are listening from tonight. Are you somewhere with a clear view of the sky? Or are clouds, buildings, and streetlights keeping most of the stars hidden? Have you ever looked up and noticed a point of light moving in a way you could not immediately explain? Perhaps it turned out to be an aircraft. Perhaps it was a satellite. Perhaps it was a bright planet near the horizon. Or perhaps you never found out and eventually went inside because it was cold and the kettle had finished boiling. That last option has probably ended more investigations of unexplained aerial phenomena than official secrecy ever has. If you find these slow journeys through science useful, you can give the video a like and subscribe to the channel. It helps other tired and curious people find this quiet corner. You can also leave a comment telling us what time it is where you are and whether you have ever seen something unusual in the night sky. Now make yourself comfortable, lower the brightness of the room if you can, and let us begin with the part of this story that is easiest to overlook. The evidence did not arrive as a clear photograph of a craft. There was no sharp outline, no visible window, no message, and no helpful label attached to the object explaining where it came from. What researchers had were small marks on old astronomical plates. These marks had to be measured, compared, filtered, and interpreted. Before anyone could discuss aliens, they first had to answer a much less exciting question. Were the marks real astronomical events at all? This is important because photographic plates are not perfect witnesses. A glass plate can preserve information for many decades, but it can also preserve scratches, dust, chemical irregularities, fingerprints, static discharges, and defects created during development or storage. A tiny patch of damaged emulsion can resemble a star. A speck of dust can block light in one place and create an apparent difference when images are compared. A flaw may look round enough to be convincing, especially when the object being studied is already expected to appear as a small point. Modern astronomy has its own problems, but digital detectors allow researchers to inspect many details about an observation. They can compare pixels, check sensor behavior, review exact timestamps, analyze several wavelengths, and often examine repeated exposures taken only seconds or minutes apart. Old plates offer less information. They record what reached the plate during a particular exposure, but they do not always tell us how a suspicious mark was created. This makes the Palomar material valuable and frustrating at the same time. The plates capture the sky before the beginning of the satellite age. That gives them a unique role. If researchers want to know whether unusual reflective objects were present near Earth before Sputnik, these records may be among the few places where evidence could exist. At the same time, the plates were not designed to answer that question. The astronomers who created them were mapping the sky. They were not running a controlled search for nearby reflective objects. They did not arrange the observations to test whether flashes disappeared inside Earth's shadow. They did not coordinate the telescope with reports of unusual objects in the atmosphere. They were not expecting future researchers to compare the plates with databases of nuclear tests, UFO reports, and orbital geometry. The data were gathered for one purpose and later used for another. This is common in science. Old records frequently become useful in ways their creators could not have predicted. It is also risky, because patterns can appear when many different datasets are placed beside one another. Suppose you have thousands of photographs, many years of observation dates, numerous reports of unidentified objects, records of nuclear tests, changing weather conditions, different telescope schedules, and several possible ways to define a transient. With enough combinations, some events may appear to line up. The difficult question is whether the alignment is stronger than chance. That is where this story becomes more serious than a collection of strange dots. Villarroel and her colleagues did not simply point to a few marks and declare them mysterious. They attempted to test whether the transients followed patterns expected from sunlight reflecting off nearby objects, One argument involved Earth's shadow. An object orbiting Earth can reflect sunlight only when sunlight reaches it. When the object passes into the shadow cast by Earth, the reflection should disappear. This is why many satellites are easiest to see shortly after sunset or before sunrise. The observer is standing in darkness, but the satellite is still high enough to remain illuminated by the sun. If the old transients were caused by reflective objects near Earth, they might be less common in regions or at times when those objects would be inside the planet's shadow. The researchers reported such a reduction. They also examined whether the transients appeared more often near dates when people reported unidentified flying objects. Again, they claimed to find an increase. A further comparison involved atmospheric nuclear tests. The team reported that transient activity rose after some tests, raising the possibility that something in near-Earth space responded to, observed, or coincidentally appeared around those events. It is easy to understand why this attracted attention. A reflective object before Sputnik is interesting. A group of reflective objects that seems to avoid Earth's shadow is more interesting. A connection with UFO reports adds another layer. A possible increase after nuclear tests moves the story into territory that has been part of UFO culture for decades. Reports of unusual aerial activity near nuclear facilities, weapons tests, and military sites have circulated for many years. Some witnesses have been sincere and experienced. Some cases remain unexplained. Others have been linked to aircraft, balloons, classified technology, astronomical objects, mistakes, rumours, or stories that became more dramatic with repetition. Placing the Palomar transients beside nuclear testing records therefore creates a powerful suggestion. It hints that unknown technology may have been present near Earth and may have shown interest in human nuclear activity before the official beginning of the space age. A suggestion, however, is not the same as a demonstration. This distinction will matter throughout our discussion. When people hear the phrase "strongest evidence of aliens yet," they may imagine a discovery that leaves almost no room for doubt. In science, the phrase can mean something much more modest. It may refer to evidence that is stronger than previous weak clues, while still being far from conclusive. Imagine 3 footprints in soft ground. One resembles the print of an unfamiliar animal. The second appears nearby. The third points toward the trees. This may be the strongest evidence you have ever found that the animal lives in the area. It is still possible that the marks were made by damaged shoes, erosion, or someone with a rather unusual sense of humour. The strength of evidence depends on what it is being compared with. For intelligent extraterrestrial life, our existing evidence is limited. We have no confirmed alien signal, no verified alien object, no biological sample, and no public observation that has been independently shown to require non-human technology. We have interesting radio signals that did not repeat. We have unusual astronomical objects that later received natural explanations. We have planets in locations where liquid water might exist. We have organic molecules in space. We have military videos showing objects that were not immediately identified. We have witness testimony, radar cases, photographs, and stories with varying levels of documentation. None of these has crossed the line into proof. The Palomar transients enter this crowded field as another possible clue. Their advantage is that the plates exist. They can be inspected. The dates can be checked. The positions of the sources can be measured. The statistical methods can be challenged. Other researchers can attempt to reproduce the findings. Their weakness is that the plates are old, imperfect, and open to several competing explanations. There's also a problem with the phrase "before Sputnik." Sputnik was the first successful artificial satellite placed into Earth orbit and publicly recognized as such. It was not the first human object to reach extreme altitude. Rockets had already traveled beyond much of the atmosphere. Military programs used high-altitude balloons. Experimental vehicles and classified projects were active. Some of these activities were poorly documented at the time, and some remain difficult to reconstruct. That does not automatically explain the transients, but it means that pre-Sputnik does not necessarily mean pre-technology. The sky of the early 1950s was quieter than the sky today, but it was not untouched. Aircraft were becoming faster, rocket research was advancing, balloons carried instruments to remarkable heights. Governments were testing systems that ordinary observers were not expected to recognize. Reflections from such objects could produce reports that sounded extraordinary, especially when viewed briefly and without reliable distance information. A bright point in the sky does not announce whether it is 10 kilometers away, 1,000 kilometers away, or many light years away. The human eye receives light, not a convenient distance label. The photographic plates had the same problem. A point source could be a distant star, a nearby body, a defect in the emulsion, or a momentary reflection. Shape alone may not settle the matter. Researchers must look for indirect clues. Brightness, duration, position, repetition, distribution, timing, and relationship to expected physical conditions. Each clue adds information, but each also introduces assumptions. For instance, a reduction inside Earth's shadow sounds persuasive only if the shadow calculation matches the true location and distance of the proposed objects. If the objects were much lower, much higher, or not near Earth at all, the expected pattern would change. A connection with UFO reports depends on how those reports were collected, filtered, dated, and distributed. Reports may increase during periods of public attention. Newspapers may encourage more witnesses to come forward. Military activity may create both unusual lights and heightened observation. A widely discussed sighting can cause people to watch the sky more carefully and report ordinary objects they would normally ignore. Nuclear tests also occurred within broader periods of military activity. Those periods may have included balloons, aircraft, tracking operations, security measures, and changes in telescope scheduling. Solar activity can influence the upper atmosphere and affect photographic observations. Seasonal conditions can alter when and where telescopes operate. A pattern can be real while its proposed cause is wrong. This is one of the most useful lessons in science. Researchers may correctly detect that two things are connected and still misunderstand why. Ice cream sales and sunburn cases rise together, but ice cream does not damage the skin. Both increase during warm, sunny weather. In the same way, transient lights and nuclear tests might rise around the same dates because of a third factor. That factor could be military monitoring, balloon launches, atmospheric changes, observation schedules, or a feature of the dataset that has not yet been recognized. It could also be something more unusual. Science does not require us to reject an extraordinary possibility simply because it is extraordinary. It requires the evidence to carry more weight when the claim becomes harder to reconcile with established knowledge. Alien technology near Earth before Sputnik would be an extraordinary claim. To accept it, researchers would want several independent forms of evidence. They might look for the same object on multiple plates taken at different observatories. They would want a clear path across the sky, consistent brightness changes, and geometry matching reflection from a moving body. They might search historical radar records, military tracking logs, balloon data, and other astronomical archives. They would try to rule out defects using blind tests. Independent teams would need to reproduce the statistical patterns. Ideally, there would be something less ambiguous than a single point of light. That standard may sound demanding, but it protects us from a very human habit. Once a possible explanation becomes exciting, the mind begins organizing every uncertain detail around it. A flash becomes a craft. A cluster becomes a formation. A coincidence becomes a response. Missing information becomes secrecy. Criticism becomes resistance. Soon, the original observation is buried beneath a much larger story. The opposite habit can be just as misleading. A skeptic may see the words UFO or alien and assume the entire subject is nonsense before examining the data. A plate defect becomes the answer even when no defect has been demonstrated. A statistical concern becomes a complete dismissal. Genuine anomalies may be ignored because the proposed explanation feels socially uncomfortable. Good investigation requires an awkward balance. We must be curious without becoming careless and cautious without becoming closed. That is the approach we will take tonight. We will look at what was found on the Palomar plates, how those plates were created, why the years before Sputnik matter, and how the VASCO team selected the sources they considered unusual. We will examine the group of 349 transients and the argument that some behaved as reflected sunlight might behave. We will also slow down around the criticisms. We will consider photographic defects, contamination, emulsion damage, poor filtering, observation bias, telescope scheduling, balloon programs, solar activity, and statistical choices. None of these explanations should be accepted merely because it sounds ordinary. Each must fit the evidence. The same rule applies to alien technology. A non-human explanation cannot win simply by surviving after the easy options are removed. Unexplained does not automatically mean extraterrestrial. It means the explanation is not yet established. For now, picture the situation as it existed before any public controversy began. A large telescope stands on Palomar Mountain. During the night, astronomers guide it toward carefully selected regions of the sky. Glass plates are placed into position. Exposures begin. Starlight enters the instrument and leaves a chemical record. The astronomers finish their work. The plates are developed, labelled, stored, copied, and studied. Years pass. Sputnik crosses the sky. More satellites follow. Human spaceflight begins. Digital astronomy replaces much of the old photographic process. The glass plates remain in archives, holding far more information than anyone has time to examine. Then new researchers return to them with a question their creators were never trying to answer. They are not searching only for stars. They are searching for things that appeared once and were never seen again. Today, when an observatory takes an image, the light usually falls on a digital detector. The result can be examined almost immediately. Astronomers can enlarge it, measure individual pixels, compare several exposures, check the detector's behavior, review the precise observing time, and search other databases while the telescope is still operating. When something unusual appears, there may be enough time to point another instrument towards it and collect more information. The astronomers working at Palomar in the early 1950s did not have that convenience. They used large photographic plates coated with a light-sensitive emulsion. Each plate was a physical object, roughly 35 centimeters across, thin enough to require careful handling, and large enough to record a broad section of the sky. It had to be placed inside the telescope, held in the correct position, exposed for a long period, removed without damage, and developed through a chemical process before anyone could see what had been captured. This was astronomy performed with glass, silver salts, dark rooms, handwritten labels, filing cabinets, and considerable patience. The survey used the 48-inch Ocean-Schmidt telescope at Palomar Observatory in California. A Schmidt telescope is designed to photograph a wide field rather than examine a tiny patch of sky at extreme magnification. That made it well suited to mapping large areas. The first Palomar Observatory sky survey photographed nearly the entire sky visible from the site, covering the heavens north of about -45 degrees in declination. Most of its plates were taken between 1949 and 1956, with a small remainder completed during the following 2 years. Each region was normally photographed twice. One plate was primarily sensitive to blue light, and another was primarily sensitive to red light. The exposures were often taken within about an hour of each other. The red plates could usually record sources down to around 20th magnitude, while the blue plates went slightly deeper. To the human eye, that is far beyond anything visible without a telescope. A 20th magnitude point is about as useful for casual stargazing as a grain of pepper viewed from the next county. The plates were not snapshots in the modern sense. A typical exposure lasted close to an hour. During that time, the telescope followed the sky as Earth rotated. Real stars remained in place relative to the telescope's tracking motion and gradually built up images in the emulsion. Other objects could appear differently. An asteroid might move far enough to leave a short trail. An aircraft could produce a longer streak or a sequence of marks. A meteor might cross the field quickly. A very short flash coming from one direction could leave a compact point, because it would expose the plate for only a fraction of the total observing period. That last possibility became important many decades later. A star shines during the entire exposure, so its recorded image is affected by atmospheric turbulence, changes in focus, and slight tracking errors over the full 50 minutes. A flash lasting less than a second would not experience all of those effects for nearly as long. It might therefore appear sharper and more compact than the surrounding stars. Supporters of the transient interpretation have used this fact to argue that an unusually neat point is not necessarily a defect. Critics have replied that damage to photographic material can also create marks that are too sharp, too round, or otherwise unlike genuine stellar images. Both arguments begin with the same problem. On an old photographic plate, a small circular mark does not explain how it was made. Once a plate had been developed, darkened grains in the emulsion represented the light that had reached it. Bright stars produced larger or denser images. Fainter objects produced smaller ones. Astronomers could inspect the plate directly, place it beneath a measuring machine, compare it with another exposure, or create copies for use at other institutions. Those copies became a standard astronomical resource. For decades, observatories around the world used Palomar survey plates as reference maps of the sky. Long before anyone could open an astronomy website and search a region in seconds, a set of Palomar images offered one of the best available records of where objects were located and how bright they appeared. The copying process is now one of the most important parts of the mystery. The original Palomar plates were valuable and delicate. They could not be mailed around the world every time another observatory wanted to inspect a field. Copy sets were therefore produced. This was not the same as duplicating a digital file. An original photographic negative could be used to make an intermediate positive. That positive could then be used to create another negative on glass. Copies made in this way could be distributed to observatories and later placed in scanning machines. Each physical stage introduced another opportunity for something to go wrong. Dust could become trapped between surfaces. A bubble could form in an emulsion. A small hole could develop. Glass might be scratched. Pressure could damage the coating. Contact printing could preserve an irregularity that had not existed on the original plate. Years later, many widely used digital versions of the first Palomar survey were created by scanning glass copies rather than the original negatives. Two digital archives might appear independent because the plates were scanned by different machines, in different countries, using different software. Yet if those glass copies had been produced from the same intermediate positive, a defect introduced during the copying process could appear in both digital scans. This matters because one method of rejecting scanning artifacts is to check whether a suspicious source appears in more than one digitization. Suppose a bright point appears in a scan produced in the United States. A second scan made from another glass plate in Britain contains the same point at the same location. That comparison can show that one particular scanner did not invent the feature. It does not necessarily prove that the feature was present in the sky. Both glass copies may have inherited the mark from an earlier shared stage. Imagine making two photocopies from the same page after a crumb has become stuck to the copying glass. The two pages are separate products, but both contain the same dark shape. Comparing them confirms that neither sheet developed the mark after leaving the machine. It does not confirm that the crumb belonged to the original document. The Palomar case is more complicated than a crumb, partly because many of the suspicious marks resemble stars. Some are compact, roughly circular, and have brightness profiles that appear plausible. They are not always obvious scratches, broad stains, or oddly shaped patches. A person examining the plate casually might never notice anything unusual until the same position was compared with other surveys. That comparison is a central part of the VASCO project. VASCO stands for Vanishing and Appearing Sources During a Century of Observations. Its researchers use old and modern sky surveys to search for objects that appear in one period but cannot be found in another. A computer can begin the process by comparing catalogues containing millions or billions of detections. Researchers then inspect the surviving candidates and attempt to remove errors, known objects, and ordinary forms of variability. A source might be visible on an old red plate, but absent from a modern catalogue. Researchers can check the blue plate taken around the same time, later Palomar plates, and newer digital observations. They can search for nearby stars that may have moved, inspect the shape of the mark, and determine whether the location lies near a damaged edge or another suspicious feature. Most initial candidates do not remain mysterious. A catalogue position may be inaccurate. A faint modern counterpart may be found. A known variable star may explain the change. A moving object may be identified. A diffraction pattern, plate boundary, scratch, or scanning problem may become obvious once the larger image is examined. A smaller number survive the early filtering. The most famous case began with a red sensitive plate exposed on April 12, 1950. Within one small region, researchers identified 9 point-like sources that were not visible in other available images. The area containing them measured only about 10 arc minutes across. The sources were not present on a blue exposure taken roughly half an hour earlier. They were absent from another red plate made 6 days later. No clear versions of the same objects appeared in much deeper modern surveys, even though those surveys could detect objects considerably fainter than the points recorded in 1950. The researchers described the marks as 9 simultaneous transients. That phrase can create the wrong mental picture. It may sound as though 9 lights switched on together, remained visible for a moment, and then disappeared together. The photographic plate does not show that. The red exposure lasted for close to 50 minutes. Everything that happened during those 50 minutes was combined into a single image. A mark created in the first second and another created 40 minutes later would sit beside each other on the developed plate as though they belonged to one moment. There was no video sequence. There were no separate frames showing the first light appearing, the second moving, or the remaining points flashing in order. The plate recorded their positions and approximate photographic brightness, but it did not preserve the timing of each individual event. If the points were caused by separate flashes, their order is unknown. If a rotating object produced several reflections while moving across the field, the gaps between the marks do not directly reveal how quickly it travelled. If unrelated defects formed during processing, the plate does not record when those defects appeared either. The word simultaneous therefore means only that all 9 marks were recorded during the same exposure. That is still unusual, but it is less precise than the word may suggest. This is also why the word transient needs to be used carefully. In modern astronomy, a transient is normally a real source whose brightness changes significantly, or which appears for a limited period. A supernova is a transient. A stellar flare is a transient. The afterglow of a gamma-ray burst is a transient. On the Palomar plates, some of the marks may be better described as transient candidates. Researchers have not yet established that all of them were lights in the sky. Some could be features created in the photographic material or during the production of a copy. The distinction separates 2 different investigations. When a mark was produced by real light, astronomers must explain what emitted or reflected that light. They can consider stars, meteors, asteroids, atmospheric events, aircraft, balloons, reflections, or unknown objects. When the mark was not produced by light from the sky, researchers must explain what happened to the plate. They can consider emulsion damage, dust, static discharges, chemical contamination, scratches, radioactive particles, bubbles, pressure marks, copying defects, storage damage, or a problem introduced by scanning. One path leads towards astronomy. The other leads towards chemistry, material science, archive history, and the working habits of a photographic laboratory. Neither path is easy because some of the most useful evidence may no longer be available. Much of the research has been carried out using digitized scans and glass copy plates. The original Palomar negatives are preserved separately and have not always been available for direct microscopic study by the researchers investigating individual transients. Intermediate positives used during the copying process may no longer exist, or their locations may be unknown. The people who loaded the plates, operated the telescope, developed the exposures, created the copies, and maintained the archives are mostly no longer available to answer detailed questions about one night in 1950. An observer may have noticed that a particular plate was difficult to load. The emulsion may have looked unusual. Humidity may have been high. Something may have touched the surface during preparation or development. A copying technician may have seen a bubble or blemish that appeared too small to matter. Such details may never have entered an official record. At the time, a few tiny marks on a survey plate were not necessarily worth documenting. Each exposure contained thousands of stars. Nobody handling the plate knew that researchers more than 70 years later would inspect 9 small points and ask whether they represented reflective objects near Earth. Archival science often works this way. The main record survives, but much of the information surrounding its creation disappears. In 2024, researchers N.C. Hambley and A. Blair published a critical analysis of the famous 9 detections. They inspected Palomar glass copy plates stored at the Royal Observatory in Edinburgh and confirmed that the points were physically present on the copy plate used for one of the major digitized surveys. That showed that the 9 features were not simply added by the digital scanning software. During the same inspection, however, the researchers also found visible blemishes in the photographic emulsions. These included bubbles, holes, and other marks that could create false detections after the plates were copied and scanned. They analysed the profiles of the 9 points and compared them with normal stars and galaxies recorded on the same plates. They also trained a machine learning system to sort detections into several categories. Their classifier judged all 9 famous points as likely bad or spurious detections rather than ordinary stars. In overlapping regions of nearby plates, Hambley and Blair found many more compact marks that appeared on one plate but not another. They proposed that at least some could have been caused by small holes in an intermediate positive used during the copying process. Those holes could later appear as dark, star-like points on a negative glass copy. The proposal offered a practical explanation for one of the strangest features of the case. A mark introduced during copying could appear in more than one scan. It could be present on physical glass. It could look compact and circular. It could remain absent from every later astronomical survey because it had never existed in the sky. That seemed straightforward, but it did not end the argument. Villarroel and her colleagues challenged the idea that sharper profiles automatically identify defects. Their response was based on the difference between a star shining during a long exposure and a reflection lasting less than a second. A normal star is recorded throughout the exposure. Atmospheric turbulence and minor tracking changes broaden its image. A short flash is recorded only briefly. It may leave a smaller, more circular point because there is less time for those effects to spread the light. From that perspective, the sharpness noticed by Hambley and Blair could be evidence for a fast optical flash rather than against it. The same feature was therefore used to support opposite conclusions. Critics saw points that were too sharp to be stars. Supporters saw points that were exactly as sharp as brief flashes should be. Neither side was claiming that a clear vehicle could be seen. The disagreement concerned the shape of a few microscopic marks and the physical process most likely to create them. This is more useful than a broad argument about whether someone believes in aliens. Image profiles can be measured, historical emulsions can be tested, Brief flashes can be produced under controlled conditions. Old copying procedures can be recreated. Original plates can be compared with first-generation and second-generation copies. Scientists could expose similar photographic material to flashes lasting known fractions of a second. They could compare those marks with stars recorded during long exposures. They could then add scratches, holes, bubbles, dust, static discharges, and chemical damage to see which defects most closely resemble the Palomar points. Copying tests would be equally important. A controlled blemish could be placed on an intermediate positive. Researchers could copy it onto a negative, digitize the result, and measure whether the false point develops something resembling a stellar brightness profile. The strongest test would involve another original astronomical exposure. Suppose a second observatory photographed the same region at nearly the same time and recorded the same flash at the same celestial position. A defect on a Palomar plate could not reproduce itself on an independent original plate hundreds or thousands of kilometers away. A genuine event might. Large collections of historical plates still exist at observatories such as Harvard, Sonneberg, Lick, and other institutions. Some contain images from the same period. Searching them is difficult. The plates may use different emulsions, cover different areas, have different exposure lengths, or remain only partly digitized. Weather and scheduling reduce the chance that two observatories photograph the same region at the right time. Still, an independent match would carry much more weight than another digital scan of a related glass copy. There are also ordinary astronomical reasons why a source visible on an old plate might seem to vanish. A faint star close to the plate's detection limit could be recorded slightly brighter because of photographic noise. The modern catalogue search might use a radius too small to allow for errors in the old position. A high proper motion star could have moved. A variable object might now be too faint in the wavelength being searched. Several faint sources close together could have blended into one mark on the lower resolution plate. Even the centre assigned to a photographic point can be uncertain by several arcseconds. At modern survey resolution, a few arcseconds may contain several possible counterparts. VASCO researchers use automatic filtering and visual inspection to reduce these problems, but every filtering system makes choices. How circular must a source be? How close to a plate edge is acceptable? What range of brightness should be included? How far away can a modern counterpart be before it is considered unrelated? Which catalogues should be trusted when they disagree? How should crowded star fields be treated? How should scratches and plate blemishes be recognized automatically? A result can change when those choices change. That does not mean the researchers are deliberately selecting a preferred outcome. Every large astronomical search depends on rules. The real test is whether the final result remains stable when other reasonable rules are used. When a pattern appears only after one narrow set of filters, it may be fragile. When it survives different catalogues, different search radii, different brightness limits, different plate regions, and independent teams, it becomes harder to dismiss. Photographic emulsion adds another complication because it does not respond to light in the same simple way as a modern digital detector. Brightness measurements can be uncertain. The response may vary across a plate. Stars near the edge can look different from those near the centre. Focus changes across the wide field. Development may not be uniform. Copies can alter contrast. A scanner contributes another layer of measurement. A source that appears slightly unusual may be unusual because of where it lies on the plate, not because of what produced it. This matters when a computer begins collecting thousands or tens of thousands of possible transients. A small false positive rate can create a large catalogue of anomalies. Suppose a program examines several million marks and incorrectly accepts only 1 out of every 1,000 defects. That sounds like a very accurate system, but it can still produce thousands of false candidates. Automation makes the search possible. It also makes independent validation essential. The large number of reported candidate transients can therefore be interpreted in two opposite ways. One possibility is that the plates contain a genuine population of short flashes, that earlier astronomers never recognized. Without modern catalogues and automatic comparisons, there was no practical way to notice that a faint point had appeared only once. The other possibility is that an enormous photographic archive contains an enormous number of imperfections, and modern software is now finding them with remarkable efficiency. Both could be true. Some marks may be copying defects, others may be ordinary stars or moving solar system objects. Some may be reflections from aircraft, balloons, or other human activity. A smaller group may remain unexplained after the obvious causes are removed. Treating every candidate as though it came from the same source may hide those differences. The group of 9 points from April 1950 attracted attention because clustering seems less random than one isolated mark. A single dot can easily be blamed on a small defect. 9 compact sources within a limited area demand some explanation for why they appeared together. When they are defects, a copying or contamination process must have created a cluster. When they are flashes, an event or group of objects must have produced several brief lights within the same field. The original investigation considered contamination, elementary particles, scanning errors, double exposure, and other possible causes. It did not claim to have eliminated every ordinary explanation. Instead, the researchers wrote that if contamination could be fully excluded, fast reflections from objects near geosynchronous orbit would be one possible explanation. That condition carries much of the weight. If contamination can be fully excluded, the words are simple, meeting the requirement is not. A plate may appear clean during one inspection and still contain microscopic damage. A copied defect may look too neat to seem accidental. A genuine flash and a small emulsion hole may produce overlapping brightness profiles. Missing records may make it impossible to reconstruct every stage through which a plate passed. The glass does not yet give a clear verdict. It gives us a collection of marks and an incomplete history of how those marks reach the digital archives. Researchers who see possible reflections are not looking at a photograph of a machine. They are looking at evidence that may be several physical generations removed from the original exposure. Critics who see emulsion defects are not holding the confirmed damaged intermediate plate that produced every point. They are building an explanation from image shape, copying methods, and the large number of similar marks found elsewhere. Something created the points. Either light entered the telescope from the sky, or a physical process created a convincing imitation of starlight. Both possibilities can be examined. Neither has been demonstrated for every candidate. The difference matters because the dates written on the plate labels place some of the most discussed examples in a period when the usual modern explanation for brief orbital glints should not have existed. The phrase before Sputnik sounds simple. It seems to divide history into 2 neat periods. On one side there is a clean and empty sky. On the other there are satellites, rocket stages, communication networks, and the beginning of the space age. Reality was less tidy. Sputnik 1 entered orbit on October 4, 1957. It was a polished metal sphere about the size of a beach ball, fitted with 4 long antennas, and it circled Earth while transmitting a steady radio signal. People around the world listened to its beeping. Newspapers printed its path. Amateur observers tried to see it pass overhead. The launch was public, successful, and impossible to ignore. For that reason, Sputnik is usually described as the first artificial satellite. That description is correct. It was the first human-made object known to complete repeated orbits around Earth. The word orbit is doing important work there. Long before Sputnik, human beings had already sent machines above most of the atmosphere. Rockets had crossed the boundary commonly used to mark the beginning of space. Instruments had reached heights where the sky looked black, and the curve of Earth became visible. Balloons had carried cameras, scientific equipment, and military payloads high above ordinary aircraft. Experimental vehicles had travelled on steep arcs, rising quickly and falling back again. Those objects reached space or near space, but they did not remain there. A satellite must move sideways fast enough that, while gravity pulls it downward, The surface of Earth curves away beneath it. Instead of falling directly back to the ground, it keeps missing the planet. That continuous fall is an orbit. A sounding rocket does something different. It rises, slows, reaches the top of its path, and descends. Its journey may last several minutes. A balloon may stay aloft for hours or days, but it remains inside the atmosphere and travels with the winds. An aircraft can climb high, but it still relies on the air around it. None of these is an orbiting satellite. This distinction matters because the Palomar transients have sometimes been discussed as possible reflections from objects near geosynchronous orbit. An object in geosynchronous orbit travels around Earth once every sidereal day. From the ground, its position repeats on a regular schedule. When the orbit is circular and directly above the equator, the object can appear almost motionless in the sky. Modern communication and weather satellites often use this region, roughly 36,000 kilometers above Earth's equator. Placing an object there is difficult. A rocket must provide an enormous amount of speed, control, and energy. The payload must survive launch. It must reach the correct trajectory and continue moving fast enough to avoid falling back. Nothing publicly known from the early 1950s had that ability. The rockets of the period were impressive, but they were not secretly one small adjustment away from placing a reflective machine in geosynchronous orbit. The technology grew from weapons developed during the Second World War. Germany's V-2 rocket became the most famous early example. It could climb to great altitude on a ballistic path and then fall towards its target at high speed. After the war, the United States and the Soviet Union captured V-2 hardware, documents, and specialists. Both nations began using the technology for military research and for experiments in the upper atmosphere. In 1946, a camera carried by a V-2 took photographs of Earth from an altitude far above any aircraft. Other flights measured cosmic rays, atmospheric pressure, ultraviolet radiation, and solar activity. Some carried animals, some failed on launch, some broke apart. Others returned useful data after only a few minutes above the atmosphere. From the ground, a rocket flight could create several unusual sights. Its engine could produce a bright moving flame. Fuel or exhaust might form a glowing cloud at high altitude. Separated components could tumble and reflect sunlight. Debris could follow different paths. A rocket launched near sunset might remain illuminated after the ground below had entered darkness. Any of those effects could confuse an observer. A long photographic exposure could record them as streaks, trails, diffuse patches, or isolated points, depending on speed, direction, brightness, and the amount of time the light remained visible. Still, a suborbital rocket should not normally look like a stationary point for long. It moves rapidly across the sky. If it remained bright throughout a large part of a Palomar exposure, it would be expected to leave a trail. To create a compact point, the reflection would have to be very brief. The motion would have to be aimed nearly towards or away from the telescope, or the geometry would have to compress the apparent movement. That is possible in principle, but it cannot be assumed for every candidate. Rockets also leave records, launch sites, test ranges, military programs, and scientific institutions kept schedules and reports, although many remain incomplete and some activities were classified. If a transient appeared during a known launch, the connection could be investigated. If no launch occurred anywhere capable of producing the effect, a rocket explanation would become less likely. The problem is that reconstructing every flight from the late 1940s and early 1950s is difficult. Not all records survived. Some dates were reported differently in separate sources. Classified programs were not fully documented in public. Test failures may have received little attention. A plate may have been exposed for nearly an hour, while its archive label gives only a start time or an approximate observing period. Even a small timing error can matter when comparing a fast event with a telescope exposure. Then there were balloons. Balloons are less dramatic than rockets, which may be why they are often underestimated. A large high-altitude balloon can travel above most clouds and ordinary aircraft. At night, it may be invisible. Near sunrise or sunset, its material, suspension lines, instruments or payload can catch sunlight and produce a bright reflection. A balloon can also appear to move very slowly against the stars. If it is distant and the wind carries it roughly along the observer's line of sight, its position may change only slightly during a short period. A brief glint from a rotating payload could form a compact mark on a plate rather than a long streak. The years covered by the Palomar survey overlapped with an extraordinary expansion of balloon research. The United States used high-altitude balloons for atmospheric science, cosmic ray studies, weather observation, photography, and military reconnaissance. Project Skyhook began in the late 1940s and launched enormous plastic balloons carrying instruments into the stratosphere. Some reached heights of more than 30 kilometers. From the ground, their appearance could be strange. The balloon envelope might be difficult to see, while the suspended equipment reflected light below it. Project Mogul, which began earlier, used trains of balloons and instruments intended to detect sound waves from Soviet nuclear tests. One of its balloon operations later became connected with the Roswell story after debris was found in New Mexico in 1947. Whatever a person thinks about every detail of that case, Mogul demonstrates that unusual balloon equipment was operating in the American Southwest before the first satellite launch. Other balloon programs followed. Project Moby Dick studied long-distance balloon travel. Project Genetrix later released camera-carrying balloons intended to drift over the Soviet Union and other regions. Scientific teams launched balloons from multiple locations. Military planners tested materials, tracking methods, recovery systems, and photographic equipment. A balloon did not need to pass directly over Palomar Observatory to appear in one of its plates. A bright object at high altitude could be visible from a considerable distance. The telescope was not looking for balloons, so the observer may not have noted one unless it crossed the field, obviously, or interfered with the exposure. This creates a reasonable earthly explanation for at least some brief lights. It does not automatically explain the reported statistical patterns. If hundreds of transients were caused by balloons, researchers would expect some relationship with known launch regions, prevailing winds, altitude limits, and the parts of the sky visible from Palomar. Balloon paths should not behave like objects in distant Earth orbit. Their interaction with Earth's shadow would also differ because a balloon, only tens of kilometers high, enters darkness soon after the ground beneath it. A high orbital object can remain sunlit long after sunset. That difference may help separate the two. Aircraft present another possibility. By the early 1950s, aviation was changing quickly. Jet aircraft were becoming faster and more common. Military testing took place across California and the American Southwest. Edwards Air Force Base, naval facilities, missile ranges, and aerospace manufacturers operated in the wider region. Some aircraft flew at altitudes and speeds unfamiliar to ordinary observers. A plane crossing a long exposure usually leaves a line. Navigation lights can create a dotted or broken trail. Reflections from a wing or fuselage may brighten suddenly. A plane travelling almost directly towards the telescope could show less sideways movement than expected. A very short flash might appear compact. The telescope's narrow view of any one point in the sky also matters. The photographic plate covered a wide field by astronomical standards, but an aircraft might enter and leave a small region quickly. If only one strong reflection occurred, the plate might preserve little more than a dot. Even so, aircraft explanations face the same need for consistency. The altitude is limited. The apparent brightness changes with distance and angle. The distribution should be influenced by routes, bases, and local activity. The plate should sometimes show trails or repeated flashes. If the candidate sources are spread across the survey in ways that do not match aviation patterns, aircraft become less convincing as a general answer. One should also remember that the telescope did not photograph the entire visible sky at once. Each plate covered a selected field. observers chose when to expose it. Weather, moon brightness, seasonal visibility, survey priorities, and technical problems all influenced the schedule. A military test or balloon launch might happen on a night when Palomar was closed by clouds. Another event might coincide with several exposures simply because the telescope was operating for many hours. This makes raw coincidence difficult to interpret. A report that a transient appeared on the same date as an unusual aerial sighting sounds meaningful. To judge it properly, we need to know how many plates were taken on ordinary dates, how many sightings were reported during the same period, and how often random dates would overlap. The same caution applies to balloons, rockets, and nuclear tests. Before moving to those statistical questions, there is one more category to consider: natural objects. The pre-Sputnik sky contained no artificial satellites, but it was never empty. Meteors entered the atmosphere constantly. Most were too faint or too brief to attract attention. A bright meteor could cross a photographic plate as a streak. A meteor directed almost along the telescope's line of sight could appear shorter. Fragmentation might produce several points or flashes. Persistent trains could remain visible after the meteor itself had vanished. Asteroids moved against the background stars. During a long exposure, a nearby asteroid might leave a short line or appear at a different position on the red and blue plates. At the survey's photographic limits, a faint trail could be broken into separate detections by defects, grain noise, or scanning software. Comets, variable stars, flare stars, novae, and other astronomical sources could also brighten and fade. Most would not disappear permanently without leaving some modern counterpart, but unusual stellar events deserve consideration before nearby technology is proposed. Cosmic rays can strike photographic material and create marks. Radioactive contamination in glass or emulsion can produce spots. Charged particles may leave tracks or localized exposures. These are not objects in the sky at all, but they are natural physical events capable of creating false astronomical sources. The sun adds further complications. Solar activity affects Earth's upper atmosphere and magnetic environment. Auroral emissions can occur at high latitudes. Energetic particles may interact with detectors and photographic materials. Changes in the ionosphere can influence radio reports and military observations. Periods of strong solar activity may also affect how often people watch the sky, or how instruments behave. None of this makes the Palomar transients uninteresting. It shows why the claim needs careful wording. Before Sputnik, there were no confirmed artificial satellites in stable Earth orbit. That does not mean there were no human-made objects above the clouds. It does not mean every brief light had to be astronomical. It does not mean the atmosphere was free of military experiments. It does not mean photographic plates were protected from particles, chemicals, dust, or damage. The phrase "nothing should have been up there" is useful as a headline, but it is too broad as a scientific statement. Plenty of things were up there. The more precise question is whether anything capable of producing repeated, compact sunlight-like reflections was moving at orbital distances before October 1957. That is a much harder claim to explain with balloons or sounding rockets. A balloon may reflect sunlight, but it does not remain illuminated under the same conditions as a high satellite. A rocket component may tumble and flash, but it stays above the atmosphere only briefly. An aircraft may create a glint, but it moves through a local region and should often leave other signs. A meteor may flash, but it does not behave like a durable reflective object circling Earth. If the transients truly follow orbital illumination geometry, then ordinary pre-Sputnik activity becomes less satisfying. The word "if" remains essential. Researchers first have to establish that the detections are real light events. They then have to show that their timing and distribution fit near-Earth reflections better than plate defects, atmospheric objects, or selection effects. Only after those steps would it make sense to ask who made the reflectors. There is also a tempting possibility that some nation placed an object into orbit secretly before Sputnik and never announced it. This idea appears occasionally in discussions of the plates. It sounds plausible because the early Cold War involved classified weapons programs, hidden test flights, and intense competition between the United States and the Soviet Union. Secrecy can conceal a great deal. Orbital mechanics is less cooperative. Launching even a small satellite requires a powerful rocket, a guidance system, a launch site, tracking, fuel production, engineering teams, and repeated tests. Failures are visible. Rockets produce exhaust, sound, debris, and records. An object in orbit may be detected by radar and optical tracking stations belonging to other countries. By the mid-1950s, both major powers were openly working towards satellites. The United States developed Project Vanguard and considered military alternatives. The Soviet Union developed the R-7 rocket that eventually launched Sputnik. Both programs faced technical difficulties in public and private. A secret earlier success is not physically impossible, but there is no accepted historical evidence for one. A secret satellite in low Earth orbit would also decay eventually unless placed high enough to survive. A large reflective object in a long-lasting orbit might have been detected after Sputnik when global tracking networks expanded. If it remained in a very high orbit, reaching that orbit would have required an even more demanding launch. The secret human explanation therefore creates its own questions. Who launched it? From where? With which rocket? How was it tracked? Why did no rival detect and expose it? What happened to it later? A solution that requires an undocumented satellite program may not be much simpler than the mystery it is meant to solve. Still, secrecy cannot be dismissed completely when the period involved military technology. Historical records can remain classified for decades. Programs may use misleading names. Flights may be described incompletely. Equipment can be lost. Governments do not always preserve tidy archives for future astronomers. The right approach is to search for evidence rather than assume either perfect secrecy or perfect disclosure. Researchers can compare plate times with known rocket launches, balloon campaigns, aircraft tests, and military operations. They can examine whether candidate lights cluster near launch corridors or test regions. They can calculate how fast an object at each possible altitude would cross the plate. They can ask whether a reflection lasting a fraction of a second could produce the measured brightness. A useful calculation begins with motion. A low satellite crosses the sky quickly. During a 50-minute exposure, a continuously visible one would create a long trail. To appear as a point, it must flash briefly. A geosynchronous object moves much more slowly against the stars, especially near the celestial equator. A steady object could still leave a small trail because the telescope tracks the stars rather than the satellite's exact motion. A brief glint could appear compact. A balloon moves more slowly still, but because it is much closer, even a modest physical speed can produce noticeable angular motion. Its apparent path depends strongly on distance and direction. These geometries can be modelled. Brightness can be modelled too. A flat reflective surface may produce a sharp flash when the sun, object, and telescope briefly align. A curved surface may create a broader glint. A tumbling object may flash repeatedly. The interval between flashes can reveal rotation. The brightness depends on size, material, distance, and the angle of reflection. Modern satellite observers see such effects regularly. A satellite that is normally invisible can suddenly brighten and then fade. Tumbling rocket bodies create repeating flashes. Small pieces of debris can produce short glints. Before dense satellite constellations filled the sky, such events were rarer, but the basic physics was the same. The VASCO argument begins by asking whether some pre-Sputnik marks resemble that modern behaviour. If the answer is yes, the historical absence of known satellites becomes significant. If the answer is no, the date may be little more than an attention-grabbing feature of an old photographic defect. This is why the years from 1949 to 1957 are so valuable. They form a natural dividing line. After Sputnik, a brief orbital reflection has an obvious human source. Each year that followed added more satellites and more debris. Before Sputnik, that explanation should be absent unless history is incomplete in a major way. An unexplained glint from 1965 is interesting. An otherwise identical glint from 1950 is more difficult. The date does not prove that the earlier glint was non-human. It removes one familiar explanation and forces the alternatives to work harder. The Palomar plates therefore provide something close to a control period for the satellite age. They record the sky before orbital space became crowded. That is exactly why Villarroel and her colleagues returned to them. That larger search began with a question that sounds straightforward until someone tries to answer it properly. Can a star disappear? Astronomers regularly watch stars change. Some brighten and fade, some pulse at predictable intervals, some erupt, shed material, or become hidden behind dust. Massive stars can explode as supernova, leaving behind neutron stars or black holes. Smaller stars may end as white dwarfs after changes lasting far longer than a human lifetime. A star vanishing completely, without an expected explosion and without a detectable remnant, would be much harder to explain. It was this type of absence that interested Beatriz Villarroel. Villarroel is an astronomer who trained at Uppsala University in Sweden. Her doctoral research focused mainly on active galactic nuclei, the extremely bright central regions of galaxies powered by matter falling towards supermassive black holes. Her 2017 doctorate examined how these galactic centres appear in large astronomical surveys, but the final paper included in her thesis introduced a different kind of search, looking through old and modern images for stars or galaxies that seem to have disappeared. She currently works in astrophysics as an assistant professor at the Nordic Institute for Theoretical Physics, known as Nordita. This was not a sudden move from ordinary astronomy into a hunt for spacecraft. The original idea belonged to a wider field known as time-domain astronomy. Instead of treating the sky as a fixed picture, time-domain astronomers compare observations made at different moments. They search for changes. A star may become brighter, a galaxy may produce a supernova, a black hole may tear apart a passing star, an asteroid may move between images, a source may appear briefly and never return. Most of these changes are natural. Some are common enough to be recognized automatically. Others are rare enough that finding even one example can improve our understanding of how stars, galaxies, and black holes behave. Villarroel's approach placed special attention on a category that astronomers might normally treat as an error. Something was recorded in an old catalogue, but it was missing from a newer and deeper survey. This is sometimes called an anti-transient search. A normal transient appears where nothing obvious was seen before. An anti-transient seems to do the reverse. It is present in the earlier observation and absent later. The first assumption should not be that the object has physically ceased to exist. A catalogue can contain mistakes. A photographic plate can contain defects. A star can move. The older coordinates can be inaccurate. A faint source may lie below the limit of a particular modern survey. A crowded patch of sky can confuse the software. Two nearby stars can be blended into one old photographic image and separated in a newer one. Different surveys also observe different wavelengths, so a source that is easy to see in red light may be difficult to detect in blue light. There are many ways for a star to disappear from a database while continuing its normal life in the sky. VASCO was designed to work through those ordinary possibilities systematically. The name stands for Vanishing and Appearing Sources During a Century of Observations. The project began taking shape around 2017 and brought together astronomers, data scientists, software specialists, statisticians, and citizen scientists. Its stated purpose was broad. Compare observations from different periods and search for exceptional sources that appeared, vanished, or changed dramatically. The possible results range from unusual but natural stellar events to speculative signs of advanced technology. The extraterrestrial part of the idea was present from the beginning, but it was not the only reason to conduct the search. One natural target was a failed supernova. A very massive star is normally expected to end its life in a bright explosion. In some models, however, the star's core may collapse into a black hole without producing an ordinary luminous supernova. The star could fade from view with far less ceremony than expected. Astronomers would see it in earlier images, notice it missing later, and perhaps detect only a faint infrared signal from material surrounding the new black hole. That would be a major discovery, even if no aliens had been inconvenienced in the process. The more speculative target involved astroengineering. A sufficiently advanced civilization might construct a large structure around a star to collect some of its energy. The best-known example is commonly called a Dyson sphere, although most realistic discussions involve swarms of orbiting collectors rather than one perfectly solid shell. Such a system could reduce the amount of visible starlight reaching us while producing excess infrared radiation as absorbed energy was released as heat. VASCO could not look at a missing star and immediately decide that a structure had been built around it. It could identify candidates that deserved additional observations. Astronomers could then search for infrared heat, unusual spectra, partial dimming, nearby counterparts, or signs that the original detection had simply been wrong. The project's researchers have repeatedly stated that none of the early candidates provided direct evidence of extraterrestrial intelligence. This careful separation is easy to lose once a story reaches the internet. Researchers search old catalogues for rare astrophysical changes is accurate, but not especially likely to interrupt anyone's breakfast. Scientists search for stars stolen by aliens travels considerably faster. The actual work was dominated by catalogues, coordinates, image cutouts, filtering rules, and visual checks. It involved less dramatic pointing towards the sky and more time looking at slightly different grey squares on a computer screen. This is a familiar feature of modern astronomy. The universe may be enormous, but a surprising amount of its investigation takes place while someone adjusts a search radius and wonders why a database has returned 40,000 unhelpful results. Villarroel, Inigo Imaz, and Josephine Bergstedt published an early version of the search in 2016. They began with roughly 10 million objects from the USNO-B1.0 catalogue that had low reported proper motion. They then examined about 290,000 objects that did not have an obvious counterpart in images from the Sloan Digital Sky Survey. The search produced many spurious entries, and one uncertain candidate considered worthy of additional observations. The authors also proposed expanding the work through citizen science, because the complete catalogue was far too large for a small team to inspect manually. Proper motion is one of the first complications in this kind of comparison. Stars appear fixed during an ordinary evening, but nearby stars slowly change position against the more distant background. The movement can be tiny, yet several decades provide enough time for some stars to travel a noticeable distance across an astronomical image. Suppose an old catalogue reports a star at one coordinate in 1952. A modern program checks exactly the same coordinate and finds nothing. That might seem like a disappearance. Search a little farther away, however, and the star may be sitting safely in its new position, having crossed the sky at a rate that would be impressive only to someone prepared to wait 70 years. Catalogues attempt to record proper motion, but old measurements can be uncertain. A scratch or plate defect may be mistakenly matched with detections from other years. Separate stars may be linked as though they were the same moving object. A true high proper motion star may have a poor estimated path. VASCO therefore had to search around each expected position, rather than compare one coordinate with another as though both were perfect. The newer survey also needed to be deeper than the older one. Imagine comparing two photographs of a dark room. The first was taken with a sensitive camera. The second was taken with a phone through a coat pocket. A lamp visible in the first and absent from the second has not necessarily vanished. The second image may simply be worse. Pan-stars provided an important modern comparison because it generally reached fainter objects than the old photographic material. The first major VASCO study compared around 600 million entries from the USNO-B1.0 catalogue, which was built partly from photographic surveys, with the first Pan-STARRS data release. The older catalogue reached roughly magnitude 20 to 21, while Pan-STARRS reached about magnitude 23.4 in the relevant comparison. A difference of several magnitudes means the newer survey could detect objects many times fainter than the older plates. That depth reduced one simple explanation. When a clear old source was absent from a much deeper modern survey, it was harder to say that the newer telescope merely failed to see it. Harder did not mean impossible. The older new surveys used different instruments, filters, exposure methods, image resolutions, and processing systems. A very red object might appear strongly on one old plate while being weak in another band. A star near a bright neighbour might be hidden by glare. A modern catalogue might exclude a real detection because its shape failed an automatic quality test. The sky position might fall into a gap-damaged region or area with poor coverage. An unmatched catalogue entry was therefore the beginning of the investigation, not the result. The large comparison produced about 150,000 preliminary candidates with no Pan-STARRS counterpart within 30 arcseconds. 30 arcseconds is a small angle in daily life, but it is generous in modern positional astronomy. It gave room for old coordinate errors and moderate stellar movement while avoiding an endless search through unrelated sources. Even after this broad comparison, the researchers found that the candidates tended to be redder and to have larger reported proper motions than ordinary catalogue objects, both signs that many apparent disappearances could arise from predictable selection effects. The number 150,000 may sound as though the team discovered a population of missing stars large enough to leave the Milky Way looking rather underfurnished. They did not. These were preliminary candidates generated before detailed visual inspection. Most were expected to be errors, mismatches, moving stars, image defects, or sources that could be found once the surrounding field was examined carefully. A useful comparison would be an airport security scanner. The machine may flag hundreds of bags. Most contain keys, cables, coins, or a regrettably dense sandwich. The purpose of the flag is not to declare every bag dangerous. It tells a human inspector where to look more closely. VASCO's catalogue comparison performed a similar job, although the sandwiches were usually plate scratches. Researchers visually inspected a subset of about 24,000 candidates. For each one, they could examine the older images, the modern survey, nearby sources and detections in different filters or epochs. A genuine point on one plate might reveal itself as part of a long scratch when the surrounding region was enlarged. A supposedly missing source might be found a few arcseconds away. A bright mark might appear only in the catalogue and not look convincing on the underlying image. This stage reduced the sample dramatically. Around 100 point-like sources remained visible in only one old red epoch and lacked obvious modern counterparts. The researchers suggested that these could include strong flares from small red stars, distant supernovae, or other unidentified red transients. Uppsala University's summary of the study noted that some appear to have brightened by at least 8 or 9 magnitudes, which corresponds to an increase of several thousand times in apparent brightness. The team also stressed that these events had not displayed direct signs of extraterrestrial technology and were thought likely to be natural, although extreme, astrophysical sources. An M-dwarf flare is a good example of why a one-time point may look more mysterious than it is. M-dwarfs are small, cool, red stars. Many are magnetically active. They can release powerful flares that briefly increase their brightness. A faint M-dwarf may be invisible in an ordinary old exposure, then flare strongly during one red plate and return to a level below the plate's detection limit. Decades later, a modern survey may contain the quiet star, but it may be faint, offset slightly, blended with something nearby, or absent from the particular catalogue used in the comparison. A distant supernova creates another possibility. A star explodes inside a galaxy too faint to be obvious on the old plate. During the explosion, the temporary point becomes visible. Later, the supernova fades. A modern deep image may reveal a weak host galaxy near the same position. or it may show nothing obvious without further observations. These examples explain why VASCO was not simply a search for objects that had been removed from the universe. It was a search for extreme changes. The project's name includes both vanishing and appearing sources, because the direction of comparison depends on which image is treated as the starting point. An object recorded in 1950 and absent today appears to have vanished. From another perspective, it may have appeared briefly in 1950. This became especially important for the Palomar transients. A star that remained visible for years and then disappeared would be one kind of phenomenon. A flash lasting less than the time separating two photographic plates would be something else. VASCO began with the broad problem of missing catalogue objects, but the old Palomar images contained candidates that may have existed for less than an hour. The search was gradually moving from missing stars to brief lights. Before reaching those lights, the researchers had to confront the limits of automated filtering. A computer is excellent at comparing coordinates millions of times without becoming distracted, hungry, or personally offended by a badly formatted catalogue. It is less reliable when asked whether a fuzzy mark looks like a star, a stain, a scratch, or the edge of a photographic defect. Machine learning systems can be trained to recognize these shapes, but they learn from labeled examples. Someone must decide which marks belong in each category. When the training examples are imperfect, the program can reproduce the same uncertainty at a much larger scale. Human volunteers provided another form of inspection. VASCO developed a citizen science effort in which participants could examine old and modern image cutouts and help classify candidates. The project worked with information technology researchers and astronomy groups in several countries. Citizen science was useful because the candidate pool was large, and because the human eye remained surprisingly effective at noticing patterns, asymmetries, nearby streaks, and obvious image problems. It also created a need for agreement. One volunteer might see a convincing star, another might see a defect, a third might click the wrong button because the cat has walked across the keyboard. Researchers can manage this by showing each candidate to several people, comparing classifications, inserting known examples, and giving more weight to consistent observers. Citizen science does not replace professional analysis. It helps reduce a huge data set to a smaller group that specialists can examine. Villarroel's role was not limited to looking through images herself. VASCO required collaboration across astronomy, machine learning, statistics, database engineering, and follow-up observation. The 2020 paper included more than 20 authors from several institutions, reflecting how quickly a simple question becomes technically complicated when it is applied to hundreds of millions of sources. Her willingness to include extraterrestrial technology among the possible long-term outcomes made the project controversial. Some astronomers regard technosignature searches as a legitimate extension of astrophysics. We know technology can alter a planet, generate radio signals, produce lasers, place objects in orbit, and change how energy is used. Searching for observable signs of similar activity elsewhere is scientifically reasonable, provided ordinary explanations are examined first. Others worry that weak anomalies can be pushed too quickly towards alien interpretations. A missing point on a plate is many steps away from a constructed object. Public attention can encourage the most dramatic explanation before the underlying data have been checked. Once the word alien appears in a headline, later corrections tend to travel at the speed of a mildly tired tortoise. Villarroel and her collaborators have argued for using anomalies as starting points rather than conclusions. In a later paper on the role of anomalies in searches for extraterrestrial life, Villarroel and Geoffrey Marcy noted that unusual observations have sometimes led to genuine discoveries, while many others disappear after noise, contamination, or faulty analysis is identified. Their proposed solution was not to trust every anomaly, but to design better observations capable of testing it from several locations and, where possible, obtaining immediate follow-up data. That principle reveals the main weakness of the Palomar material. VASCO could return to the plate, but it could not return to the night. When a suspicious point was discovered 70 years later, no one could ask another telescope to look at it immediately. No spectrum could be taken. No second observer could report whether it moved. No radar operator could be told to check the same coordinate. The event, real or defective, had already finished. All that remained was the record. This is why the project's early missing star work and its later pre-Sputnik investigation should be kept separate. The first search compared old catalogue objects with modern surveys over decades. It looked for sources that may have faded, moved, or vanished. The pre-Sputnik work focused increasingly on points present in one photographic exposure, but absent in another taken shortly before or afterwards. These were not necessarily stars that had disappeared permanently. They may have been flashes lasting seconds or less. The methods also began to change. Instead of asking only whether one old object had a modern counterpart, the researchers examined how multiple brief sources were distributed. Did they occur alone or in groups? Were they concentrated near particular regions of the sky? Did they appear at times when an orbiting object would be illuminated by the sun? Did their frequency change inside Earth's shadow? Could similar marks be produced by known photographic defects? A single candidate can always be unusual by accident. A population can reveal behaviour. The systematic search produced far more than 349 possible transients. That number refers to a particularly important part of the later analysis, not to the total number of unexplained marks found on the Palomar plates. This is worth clarifying because the numbers can become confusing very quickly. The automated VASCO search initially identified 298,165 sources that appeared on the red Palomar plates, but did not have an obvious counterpart in either Gaia or Pan stars within the selected search distance. Most of those sources were not treated as mysterious for long. Researchers found infrared counterparts for 288,770 of them. They identified 189 as asteroids, 35 as variable objects, 3,592 as likely artifacts, and 180 as high proper motion objects whose movement had not been represented correctly in the Gaia information used for the comparison. After those checks, 5,399 unidentified transient candidates remained in the published catalogue. Even that smaller number did not represent 5,399 verified flashes in the sky. It represented detections that survived a particular series of automatic comparisons and filtering rules. Some may have been genuine astronomical events. Some may have been unrecognised moving objects. Some may have been photographic defects that looked sufficiently star-like to pass the software's tests. A later analysis used a broader filtered sample to examine the distribution of possible transients across the Palomar survey. The researchers required the candidates to have no counterpart within 5 arcseconds in Gaia, Pan stars, or the infrared survey NEOWISE. They also limited the study to the northern celestial hemisphere. This produced a working sample of 106,339 detections. Of those 106,339 detections, 349 fell inside the region where Earth's shadow would have been located if the proposed reflecting objects were at the distance of geosynchronous orbit. The number 349 therefore became important because it was unexpectedly small. It was not a collection of 349 lights that all appeared together. It was not a carefully photographed formation. It was not 349 objects tracked as they travelled around Earth. It was the number of candidate transients found in one geometrically defined part of the sky, compared with more than 100,000 candidates outside it. That comparison formed one of the strongest arguments offered by Villarroel and her colleagues. If the points were distributed randomly, and if Earth's shadow covered the fraction of sky assumed in their first calculation, many more than 349 should have appeared inside the shadow. The observed shortage suggested that the events occurred more often where sunlight was available. A plate defect should not care whether a location in the sky was illuminated by the sun. A scratch does not check orbital geometry before appearing. A bubble in an emulsion does not wait for sunrise. A reflection does. This is the central reason the researchers became interested in glints. A glint is a brief flash caused when a reflective surface sends sunlight towards an observer. Most objects do not reflect light equally in every direction. A rough surface scatters light broadly. A smooth or flat surface can direct a much stronger reflection along a narrow path. The effect is familiar on Earth. A distant window may suddenly produce a bright flash when the angle between the sun, the glass and your eyes becomes just right. Move a few steps and the flash disappears. A car windscreen can do the same thing. So can a phone screen, a polished roof, or the watch of someone who has accidentally found an efficient way to signal across an entire park. Nothing about the object itself has switched on. The geometry has changed. An object in orbit can produce the same effect. Solar panels, insulation, flat metal surfaces, mirrors, and pieces of debris may reflect sunlight. As the object moves or rotates, the reflection can sweep across Earth. An observer sees a flash that lasts for a fraction of a second and then vanishes. Modern high-speed observations show that these events are common. One survey using a telescope that recorded 25 images per second detected flashes lasting roughly 1/10 to 3/10 of a second. The researchers concluded that most, and possibly all, were sunlight glints from satellites in geosynchronous or graveyard orbits. Those very short flashes can look like point sources rather than trails, particularly when they are recorded in a single longer exposure. This provides a known process that can create exactly the sort of appearance that interested VASCO. A compact light source that appears in one image and is missing from the next. The problem once again is the date. A satellite glint today has a simple explanation. Thousands of functioning spacecraft and large quantities of debris orbit Earth. The sky contains flat panels, tumbling rocket bodies, damaged components, and objects whose orientation changes over time. A brief flash is not evidence that anything unknown has arrived. It is more likely evidence that human engineering has produced yet another reflective surface and placed it somewhere inconvenient for astronomers. A similar flash in 1952 cannot be explained by an ordinary satellite, because there were no confirmed human-made satellites in orbit. The VASCO researchers therefore considered a more provocative possibility. If some of the pre-Sputnik points were genuine glints from high-altitude objects, the reflecting surfaces might have been artificial but not human. That is not the only interpretation offered in the research. It is the one that attracted the most attention. Before reaching it, the investigators tried to determine whether some candidates displayed features expected from reflective objects rather than unrelated stars or random defects. One feature involved duration. The red Palomar exposures generally lasted around 45 to 50 minutes. If a source shone steadily throughout that time and moved across the sky, it should leave a trail. A compact point suggests either that the source remained fixed relative to the stars, or that it emitted or reflected light for only a short part of the exposure. A normal distant star remains fixed enough to appear point-like. It should usually remain visible on other plates or in modern surveys unless it was an unusual transient event. A nearby moving object can also appear point-like when its flash is sufficiently brief. It may travel a considerable distance during the full exposure, but the plate records it only during the fraction of a second when light reaches the telescope. Imagine walking through a dark room while someone takes a photograph with the camera shutter open for 1 minute. When you carry a continuously glowing torch, the image shows a line tracing your path. When the torch flashes once for 1/100th of a second, the photograph shows light at only one position. The image does not reveal the distance you travelled before or after that moment. The Palomar plates worked in much the same way. This creates a difficulty when estimating the location of a candidate source. A point does not tell researchers whether it was an enormous flash far away or a small reflection nearby. The brightness recorded on the plate is a combination of the object's size, reflectivity, distance, orientation, and flash duration. A highly reflective surface can appear bright for a very short time. The long photographic exposure then dilutes that flash. Suppose a glint reaches 9th magnitude for 1/10 of a second during a 50-minute exposure. The plate collects that light for only one part in 30,000 of the total exposure. When averaged across the full period, the source appears much fainter than its momentary peak. A point measured as a faint 15th or 16th magnitude source on a long plate may therefore have been briefly much brighter. This is not a special rule invented for the Palomar claims. Modern satellite glint studies must account for the same dilution. Fast cameras see the flash close to its true brightness. A conventional long exposure records only the small amount of light collected during the brief event. The shape of the point adds another clue, although it has also produced disagreement. Stars recorded during a long exposure are blurred slightly by atmospheric turbulence, guiding errors, wind, and changes in the telescope. A flash lasting a fraction of a second is exposed to those effects for much less time. It may therefore appear narrower and more circular than an ordinary stellar image. Villarroel, Enrique Solano, and Geoffrey Marcy argued that unusually sharp profiles can be consistent with very brief optical flashes. Their critics have interpreted similar sharpness as evidence that the points are defects in the photographic emulsion rather than sources in the sky. The argument cannot be settled merely by saying that a mark looks like a star. Both a real flash and a well-formed defect may look star-like at the limited resolution of a digitized plate. The researchers also became interested in groups of transients appearing within the same exposure. The famous April 1950 plate contained 9 point-like detections in a small area. Another plate exposed on July 19, 1952, contained 3 bright point sources within about 10 arcseconds of one another. They were present on the red exposure and absent from a blue exposure taken within the following hour. Much deeper observations made with the Gran Telescopio Canarias in 2023 still found no objects at those positions. A group creates different possibilities from an isolated point. Several astrophysical objects could brighten independently during the same exposure, but the chance becomes smaller when they occupy a very limited region. Gravitational lensing can create multiple images of one distant event, although the required lens structure and timing may be unusual. A fragmented asteroid might produce several pieces, but movement and trails would have to match the observations. Several plate defects might also appear close together. Damage does not have to be uniformly scattered. Dust, bubbles, pressure, copying errors, or chemical problems can create local clusters. A hair or scratch can produce a line of false detections. Diffraction features around bright stars may cause software to identify several compact points along the same direction. The VASCO team searched for groups that were not merely close but aligned. The proposed reasoning was based on a moving and rotating reflective object. As it crossed the field, each momentary alignment with the sun could produce another glint. Those glints might appear along the object's path as a row of separated points. The object itself would remain invisible between the flashes. The final plate might resemble a dotted line, although each dot could have been produced at a different moment during the exposure. This is similar to the blinking lights of an aircraft recorded in a night photograph. The aircraft moves continuously, but the image contains a sequence of bright marks separated by dark gaps. An object in high orbit would move differently and might flash because of rotation rather than navigation lights, but the basic photographic result could be similar. Villarroel and her collaborators developed statistical tests to ask whether the points in a group were more closely aligned than random positions would usually produce. Their later peer-reviewed paper reported several candidate alignments, including one assigned a statistical significance of roughly 3.9 sigma. The authors said the aligned events remained difficult to explain, while acknowledging that rare forms of optical ghosting or plate artifacts could not yet be completely excluded. A value such as 3.9 sigma does not mean there is a 3.9 sigma probability that the source was alien. It describes how unusual a measured pattern would be under a particular statistical model. That model depends on assumptions. Researchers must decide the size of the region in which alignments will be counted. They must define how close the points need to be to a straight line. They must account for the number of plates searched, the number of groups tested, and the fact that different box sizes or filtering rules might produce different candidates. When many possible patterns are examined, at least one may look unlikely by chance. This is known as the look elsewhere effect. Imagine throwing a large handful of rice onto a table. After looking carefully, you may find several grains that form a nearly straight line. The alignment can look impressive when shown by itself. Its significance depends on whether you decided to search for that exact line before throwing the rice or searched for every interesting arrangement afterwards. The same issue appears in astronomy, particle physics, medical research, finance, and almost every activity involving a sufficiently large spreadsheet. The VASCO team attempted to quantify the probability of chance alignments rather than relying on visual impressions. Critics can still question whether the model captures the real distribution of defects on photographic plates. Defects may not be independent or randomly distributed. They may cluster near edges, scratches, bright stars, copying damage, or regions where the emulsion behaved differently. A statistical test comparing the points with a perfectly random sky could exaggerate their unusualness when the true background is uneven. The survey itself is uneven too. Palomar did not photograph every part of the sky at every time with identical conditions. Plates differ in exposure quality, limiting brightness, atmospheric clarity, date, telescope pointing, and development history. Some regions contain crowded stars, others are comparatively empty. Some plates may have more defects than others. The number of candidate transients on a plate can therefore vary enormously. That variation complicates attempts to estimate a single average rate. One plate with thousands of false detections can dominate a calculation unless researchers identify and control it. A handful of damaged plates may create patterns that appear to belong to the sky as a whole. The later VASCO work tried to reduce this problem through source shape filters, catalogue comparisons, plate-by-plate checks, and more restrictive samples. The 2022 catalogue selection procedure required strong signal-to-noise, rejected obvious diffraction spike detections, limited elongation, removed objects with unusual widths, and corrected Gaia positions to identify moving stars. The authors still describe the final 5,399 sources as unidentified candidates rather than confirmed physical transients. The larger sample of 106,339 used for the shadow analysis involved a different balance. A strict catalogue of the cleanest candidates reduces contamination, but may leave too few events for strong population statistics. A larger sample provides greater statistical power, but it may include more defects in ordinary sources. Neither choice is automatically wrong. The question is whether the reported result survives when the analysis is repeated using different reasonable selections. A genuine reflection effect should remain visible when obvious damage plates are removed, when sources near bright stars are excluded, when different shape requirements are used, and when separate digitized copies are tested. A result that disappears after one minor change would be far less convincing. The researcher's argument does not depend on every point being a glint. A sample can contain many contaminants and still reveal a real subpopulation. Modern astronomical surveys regularly include satellite reflections mixed with stars, cosmic rays, detector noise, and genuine astrophysical transients. Statistical analysis can sometimes identify the behavior of one population without classifying every individual event correctly. Suppose a jar contains thousands of grey stones and a smaller number of iron beads. You may not be able to tell which is which by looking at each piece. Bring a magnet near the jar, however, and the iron population behaves differently. Earth's shadow was intended to act like that magnet. When a candidate lies outside the shadow, it may be a star, defect, reflection, or another phenomenon. When it lies inside the shadow, a sunlight reflection from the assumed orbital distance should be impossible. The comparison does not need every outside event to be a glint. It asks whether the entire population changes where sunlight is blocked. This brings us back to the 349. Using a simple geometric estimate for the shadow at geosynchronous distance, the team calculated that about 1,223 of the 106,339 transients should have fallen inside it if the detections were distributed according to the assumed sky coverage. They found 349. The difference appeared extremely significant under that first model, close to 22 sigma. A more realistic simulation considered the actual Palomar plate fields and exposure times, rather than treating the northern hemisphere as though it had been sampled uniformly. The expected shadow coverage became much smaller. In that version, about 0.53% of simulated positions fell inside the shadow, while approximately 0.32% of the observed transients did. The reported deficit was roughly 39%, with a significance of about 7.6 sigma. The study's authors described this as support for the idea that sunlight was necessary to produce a portion of the events, while presenting the work as an initial archival investigation rather than proof of extraterrestrial objects. Those numbers are intriguing. They also need to be handled carefully. A statistical significance can be very high, while the interpretation remains uncertain. A hidden bias affecting where plates were taken, which plates survived filtering, or where defects were detected could produce a strong pattern. Incorrect exposure times could shift the calculated shadow. Seasonal observing schedules could make some sky regions more likely to be photographed under particular conditions. The calculation also assumes an altitude. Earth's shadow occupies a different apparent region depending on how far away the proposed object is. A point classified as shadowed at geosynchronous distance might not be shadowed at another altitude. An atmospheric source, a low-orbit object, and a much more distant object experience different illumination geometry. The 349 are therefore not a list of identified spacecraft. They are the smaller than expected group found on the dark side of a particular orbital model. Their importance comes from the contrast with the rest of the sample. The researchers saw fewer candidate events where reflected sunlight should be unavailable. That is the sort of population behavior a glint hypothesis predicts. Whether the prediction has truly been confirmed depends on the reliability of the catalogue, the accuracy of the timing, the geometry of the observations, and the absence of another factor that follows the same pattern. The shadow calculation was intended to answer a practical question. If many of the old points were produced by sunlight reflecting from nearby objects, what should happen when Earth moved between those objects and the Sun? The reflections should stop. Earth blocks sunlight and creates a long shadow extending into space on the side opposite the Sun. An object passing through the darkest part of that shadow no longer receives direct sunlight. It may still be present. It may continue moving along exactly the same path. A telescope may remain pointed towards it. Without another source of illumination, however, the object cannot produce a bright flash by reflecting direct sunlight towards the observer. This gives astronomers a useful way to separate reflected light from other kinds of events. A star does not disappear because its position happens to lie behind Earth's orbital shadow at a particular distance. A distant supernova does not check whether a hypothetical satellite between it and the telescope is illuminated. A defect in photographic emulsion has no physical connection with the direction of the Sun. Dust, scratches, bubbles, and scanner errors should not deliberately become less common in the small area where Earth blocks sunlight. Satellite glints should. Modern transient surveys sometimes use Earth's shadow for exactly this reason. By observing within the shadow at the distance of geosynchronous satellites, researchers can greatly reduce contamination from brief reflections produced by spacecraft and orbital debris. The method does not remove every false detection, and it does not remove objects producing their own light, but it creates a region where direct solar glints should be strongly suppressed. The basic idea can be demonstrated with an ordinary object. Imagine standing in a dark room while someone shines a torch on a rotating mirror. Each time the mirror reaches the correct angle, a bright flash reaches your eyes. Now place a large book between the torch and the mirror. The mirror has not vanished, and it has not stopped rotating. It simply has no torchlight to send back. Earth plays the role of the book, although it is considerably harder to leave on a bedside table. The geometry becomes more complicated because Earth is round. The Sun is much larger than Earth. The atmosphere bends a small amount of light, and the possible reflecting objects may occupy many different altitudes. Behind Earth, there is a central region called the umbra, where the Sun is completely hidden. Around it is the penumbra, where only part of the Sun is blocked. Atmospheric refraction adds a faint outer region, where sunlight bends through the atmosphere. An object near the edge of the shadow may therefore receive some sunlight, even when a simple geometric model says that Earth should be in the way. For this reason, researchers interested in removing satellite reflections often use a conservative inner shadow, rather than treating every point near the boundary as fully dark. At the distance of geosynchronous orbit, the full shadow appears as a roughly circular patch centered near the point directly opposite the Sun. Its apparent radius is commonly estimated at about 8 or 9 degrees, with the exact value depending on the observer's position, the date, the assumed orbital distance, and whether atmospheric refraction is included. Geosynchronous orbit lies about 35,786 kilometers above Earth's surface, or roughly 42,164 kilometers from Earth's center. That distinction between altitude and distance from Earth's center is easy to miss. When someone says an object is at 42,164 kilometers, they may mean its distance from the center of Earth, not its height above the ground. The surface is already more than 6,000 kilometers from the center. Mixing those measurements changes the apparent size of the shadow and can affect how many transients are classified as illuminated or dark. The shadow also changes with distance. Close to Earth, the planet covers a larger part of the sky as seen from the object. Farther away, its apparent size becomes smaller. At low orbital altitudes, the shadow region is broad. At higher distances, it narrows. Eventually, because the Sun is wider than Earth, the darkest central shadow comes to an end. This means a transient cannot be labelled inside or outside Earth's shadow without first assuming where the source is located. A point on a Palomar plate has direction, but it does not have a measured distance. The mark tells researchers where the telescope was looking. It does not tell them whether the flash occurred inside the atmosphere, near a low satellite orbit, at geosynchronous distance, 80,000 kilometers away, near the Moon, or among the stars. Villarroel and her collaborators therefore tested specific distances. One of the most important was the geosynchronous region, because a reflecting object there could move slowly enough against the stellar background to produce compact or separated glints during a long exposure. They also tested a greater distance of about 80,000 kilometers from Earth's center. The angular shadow is smaller there, so fewer candidate positions should fall inside it. For each plate, the researchers needed the observing date, the telescope's location, the celestial coordinates of each candidate, and the position of the Sun. The point directly opposite the Sun in the sky is called the anti-solar point. The center of Earth's shadow lies near that direction, although the exact topocentric geometry depends on where the observer is standing on Earth. Using software developed to calculate the shadow, the team tested whether the line of sight to each transient would pass through the umbra at the assumed distance. The answer for each candidate was reduced to a simple classification: sunlit or shadowed. That classification was then applied to the sample of 106,339 candidate transients in the northern celestial hemisphere. The sample had been selected by requiring no nearby counterpart in Gaia, Pan-STARRS, or Neowise. It had not received complete individual visual inspection, and the researchers acknowledged that it was expected to contain substantial contamination from false positives, including clustered plate defects and marks near plate edges. They also noted that the survey's sky coverage was uneven. This may sound like a serious problem for the test. It is. It is also the reason the shadow argument was attractive. The team's reasoning was that false positives could remain in the catalogue as long as they affected the sunlit and shadowed regions in approximately the same way. A defect might add noise to both groups, but it should not create a systematic shortage specifically inside Earth's shadow. Suppose 90% of a sample consists of harmless grey stones, and 10% consists of reflective beads. Place the entire mixture in darkness, and the stones look much the same while the beads stop flashing. You do not need to identify every bead individually to detect that a reflective population exists. The shadow analysis tried to do something similar. Under an initial geometric estimate, about 1,223 of the 106,339 candidates were expected to fall within the umbra at the geosynchronous distance. The observed number was 349. That meant the catalogue contained fewer than 1/3 of the shadow detections predicted by the simple calculation. Using Poisson uncertainties, the authors described the difference as approximately 21.9 sigma. At the tested distance of 80,000 kilometers, they expected 339 shadow detections and reported 79, producing a stated significance of about 12.7 sigma. Those are enormous statistical values. In many areas of physics, a result reaching 5 sigma attracts serious attention. A 22 sigma result sounds less like a subtle clue and more like a statistic arriving at the laboratory with its own marching band. The number must still be interpreted in context. A sigma value describes how unlikely the measured difference would be under a particular statistical model. It does not measure the probability that the explanation is correct. It does not say there is a 22 sigma chance of alien spacecraft. It says that, if the assumptions used to calculate the expected number are valid, random counting variation alone is an extremely poor explanation for the difference. The assumptions are therefore where the real argument begins. The earliest expected value treated the shadow as a fraction of the relevant celestial hemisphere. That is a simple theoretical comparison. The Palomar survey, however, did not observe the entire hemisphere uniformly. Some fields were photographed more than once, others were recorded on different dates. The telescope operated only during suitable nights. Weather, seasons, moon brightness, survey planning, equipment, and the visibility of each region influenced where the plates were pointed. Earth's shadow also occupies different celestial coordinates on different dates. A patch of sky that lies inside the shadow in December may be far from it in June. If Palomar observed that patch mainly in June, it contributed no useful December shadow coverage. Counting the theoretical fraction of the whole hemisphere could therefore give the wrong expected number. The researchers addressed this with a plate-based simulation. Rather than scattering expected events uniformly across the northern sky, they placed simulated points within the actual plate fields and used the real observation times. This attempted to reproduce the areas the survey had genuinely photographed, while the shadow occupied each position. The correction substantially reduced the expected shadow fraction. In the more realistic model, approximately 0.53% of simulated positions fell inside the geosynchronous shadow. The observed fraction was around 0.33%. The deficit remained, but its reported significance fell from roughly 22 sigma to about 7.6 sigma. The published paper presented this reduced result as the more realistic estimate, and described the work as an initial exploration rather than a completed demonstration of artificial objects. A fall from 22 sigma to 7.6 sigma does not make the pattern disappear. It shows how strongly the result depends on modelling the survey correctly. The simple model predicted more than 1,200 shadow events. The plate-based approach predicted a much smaller number. The observed count of 349 therefore changed from an apparently enormous deficit to a more moderate one, although still statistically significant according to the author's analysis. This is a useful reminder that more decimal places do not make a result more reliable than the assumptions beneath them. A calculator can divide the wrong numbers with extraordinary precision. The authors argued that the remaining deficit was difficult to explain with random plate damage. Even if the catalogue contained many defects, those defects should not follow the moving position of Earth's shadow across the sky. A reduction in that region suggested that at least some of the detections depended on sunlight. If that interpretation is correct, the result would be important. It would mean the catalogue contains a population of real optical events rather than only photographic flaws. It would also mean those events behaved as reflected sunlight behaves. That conclusion still would not establish what reflected the light. High-altitude balloons, experimental vehicles, meteoric material, unusual atmospheric phenomena, and unknown human activity would remain candidates. The source distance would still be assumed rather than measured. The shape and size of the reflective surfaces would remain unknown. The shadow test would support the category reflection. It would not supply the label alien spacecraft. Several ways remain for a false deficit to appear. The first involves the accuracy of the observing times. A plate exposure often lasted between 45 and 50 minutes. Archive records may provide a start time, a midpoint, or another timestamp depending on how the information was entered and later digitized. If a shadow calculation uses the wrong part of the exposure, some candidates near the boundary could be placed on the wrong side. The center of the shadow does not race across the stars during one exposure, but topocentric geometry and the position of a candidate relative to the boundary can matter. A small error is unimportant for a source near the center of the umbra, and more important for one close to its edge. The second issue is plate assignment. A catalogue detection must be linked to the correct photographic plate before the proper observing time can be used. Overlapping survey fields can contain the same sky position. Coordinate transformations must account for the way angular separations change with declination. A small geometric mistake can assign a candidate to the wrong field or date, which then gives it the wrong shadow status. The third problem is the spatial distribution of false detections. Plate defects may not know where Earth's shadow is, but they do know where the edges of a plate are. Scratches, fingerprints, emulsion damage, vignetting, copying problems, scanner behavior, and catalogue extraction errors can become more common in particular regions. The 2026 critical analysis by Wesley Waters and colleagues reported that unidentified features increased gradually towards plate corners and edges, and included geometric clusters, empty strips, and other patterns suggestive of instrumental or processing effects. Now consider how the telescope schedule interacts with those plate patterns. If the shadow tends to fall near the center of certain observed fields, while defects are more common near their edges, a deficit can appear even though the defects have no direct knowledge of sunlight. The bias emerges from the combination of field placement, plate geometry, and observing time. Neither factor produces the result alone. Together, they can. This is why a proper comparison must preserve the actual defect distribution inside each plate, not merely the plate's overall outline. Simulated points placed uniformly across a field may fail to reproduce edge concentrations, damaged strips, crowded stellar regions, and plate-specific clusters. The fourth issue is sample purity. The 106,339 source collection was much larger than the catalogue of 5,399 more carefully filtered unidentified candidates described in the earlier VASCO work. The larger sample offered more statistical power, but it was not fully visually inspected and was expected to include known astronomical sources, scan artifacts, plate defects, and other contaminants. Waters and colleagues reported that they did not recover a significant Earth shadow deficit. when analysing a smaller and more heavily vetted dataset. They argued that the broad sample used for the strong shadow result had not been shown to consist of genuine optical transients. Villarroel and several collaborators disputed that criticism. Their response argued that the smaller dataset had been created for a different purpose, had been reduced by about a factor of 20, lacked complete timing information, and was statistically underpowered for the shadow test. They also challenged parts of the coordinate and plate assignment procedure used by the critical team, including whether the necessary cosine of declination correction had been handled consistently. They concluded that the critique did not invalidate the original result. The disagreement reveals a difficult trade-off. A very large data set provides enough candidates to detect a small population effect, but it may contain substantial contamination. A very clean dataset reduces contamination, but it may contain too few sources to reveal the effect even when the effect is real. Imagine testing whether 1% of coins in a container are magnetic. With 100,000 uninspected objects, the magnetic signal may be measurable, but the container may also include buttons, washers, pebbles, and the remains of a paperclip. With 50 carefully verified coins, the sample is clean, but there may be no magnetic coin in it by chance. The best solution is not simply to argue over which container is preferable. It is to build a large sample with reliable object-by-object validation and complete observing information. That has not yet been achieved for the Palomar candidates. A further complication is that Earth's shadow can test only a particular kind of illumination. A self-luminous object could flash inside the shadow. An electrical discharge, engine, laser, explosion, or another active source would not require direct sunlight. A natural astronomical transient far behind the assumed orbital distance would also be unaffected. Moonlight could produce reflections, although it is far weaker than sunlight. Light refracted through Earth's atmosphere can reach objects near the shadow boundary. A conservative analysis must therefore distinguish the deep central umbra from the brighter fringe. The presence of 349 candidates inside the calculated shadow is not necessarily a problem for the glint idea. Some may be defects, some may be ordinary stars, some may have been assigned incorrect times or positions, some may lie near the boundary. The hypothesis proposes that only part of the full sample consists of sunlight reflections. The relevant result is the difference in rates, not a perfectly empty shadow. This is why the researchers did not claim that all 106,339 detections represented nearby objects. Their interpretation was that a fraction of the population may depend on solar illumination, estimating that fraction is not straightforward. A roughly 40% deficit under the plate-based model does not mean exactly 40% of all candidates were glints. Detection efficiency may differ across plates. Some glints outside the shadow would still be too faint to record. Some non-reflective contaminants may also vary with observing conditions that correlate with shadow position. The safest description is that the authors reported a statistically significant shortage of candidate detections within the calculated geosynchronous shadow, while critics argue that sample contamination and survey geometry may account for some or all of it. Independent replication is the obvious next step. Another team could begin with the original plate scans, create a fully documented catalogue, publish every filtering rule, verify plate times, model each plate's defect distribution, and repeat the calculation without knowing the expected outcome while the selection is being made. Better still, researchers could use original plates from another observatory. A second archive would have different emulsions, telescope optics, copying procedures, weather, and observing schedules. When the same shadow deficit appeared there, photographic and Palomar-specific explanations would become much less convincing. Recent preliminary work using 1950s plates from Hamburg Observatory has reported narrow transient light profiles similar to those found in the Palomar material, but that analysis remains ongoing and does not by itself establish the physical origin of the marks. Modern observations can test the method more directly. Researchers know that today's sky contains satellites. They can photograph fields inside and outside the geosynchronous shadow using rapid cameras, measure how strongly glints decline, and compare the result with a simulated long photographic exposure. They can add known defects to digitized plates and determine whether the full analysis mistakenly creates a shadow pattern. Multiple telescopes separated by kilometers could observe the same flash. A nearby object would appear at slightly different positions because of parallax, while a distant star would not. The source distance could then be measured rather than assumed. The old plates cannot provide that missing information after the event. They can only preserve a statistical trace. For supporters of the glint interpretation, Earth's shadow is the most persuasive part of the case because it connects the detections with a specific physical requirement: direct sunlight. For critics, it is an example of how a strong number can emerge from an uncertain catalogue, an uneven survey, and a model that changes significantly when more realistic coverage is included. Both sides agree on one point, even when they disagree about almost everything else. The shadow result deserves a better test. Until that happens, the shortage of 349 detections remains intriguing without being decisive. It may show that some real reflective phenomenon was present in the pre-Sputnik sky. It may reveal an interaction between plate defects and the way Palomar scheduled and positioned its observations. It may contain both effects mixed together. The shadow results suggested that at least some of the candidate lights might depend on sunlight. That still left a basic question unanswered. Why would reflective objects appear on particular nights rather than others? Stephen Bruel and Beatriz Villarroel approached that question by comparing the Palomar detections with two historical records. The first contained dates of above-ground nuclear weapons tests. The second contained reports of unidentified objects seen in the sky. This was a controversial comparison from the beginning. Claims connecting UFOs with nuclear weapons have circulated for decades. Military personnel, civilian witnesses, and researchers have reported unusual objects near weapons laboratories, missile facilities, test sites, power stations, and storage areas. Some incidents have extensive documentation. Others rely on memories recorded many years later. Some have conventional explanations, while others remain disputed. The Palomar plates offered a possible source of information that did not depend on witness memory. The telescope did not know when someone had reported a UFO. The photographic emulsion did not read newspapers. Astronomers exposing the plates were not searching for alien visitors, and the brief marks were not discovered until many decades later. If the number of transients changed around nuclear tests or increased on dates with more UFO reports, that pattern could not easily be blamed on Palomar astronomers expecting to see something unusual. That was the reasoning behind the study. Bruel and Villarroel created a daily dataset covering November 19th, 1949 through April 28th, 1957. The period contained 2,718 calendar days. Transient candidates appeared on 310 of those days, or about 11.4% of the total. The number recorded on a single date ranged from 0 to 4,528, because Palomar sometimes exposed several plates covering different parts of the sky during one night. The distribution was extremely uneven. Most dates had no transients, while a small number had very large counts. The researchers compared this record with 124 dates on which the United States, the Soviet Union, or Britain conducted above-ground nuclear tests. They defined the main nuclear testing window as the test date, plus the day before and the day after. This 3-day window was selected before they examined how it matched the transient data, according to their methods. They also performed later comparisons for individual days ranging from 2 days before a test to 2 days afterwards. The first result was straightforward to describe. At least one transient was found on 15.6% of dates inside a nuclear test window. Outside those windows, at least one appeared on 10.8% of dates. The calculated relative risk was 1.45, meaning a transient was about 45% more likely to be recorded within 1 day of a nuclear test than on other dates. The reported probability value was 0.008 under the statistical test used by the authors. This does not mean that 45% of the lights were caused by nuclear weapons. It does not mean that nearly half the objects arrived to inspect a test. A relative risk increase compares two rates. The ordinary rate was about 11 transient days for every 100 dates. The nuclear window rate was about 16 for every 100. The difference is real within the dataset, but smaller than the percentage alone may make it sound. The team also compared the total number of candidates recorded on each date. Because a few dates contained thousands of detections, an ordinary average would have been heavily influenced by extreme values. The researchers used trimmed means and non-parametric tests. Dates inside nuclear windows showed a higher transient count than dates outside them. When they divided the 3-day window into individual dates, the strongest result appeared on the day after a nuclear test. Transients were found on 18.5% of those days, compared with 11% of dates that did not fall 1 day after testing. Expressed as a relative difference, the chance of recording a transient was 68% higher on the following day. None of the other individual offsets reached significance in that part of the analysis. The delay made the result harder to explain in a simple physical way. A nuclear explosion produces light, heat, radiation, shock waves, dust, and debris immediately. A telescope pointed towards the correct region during the event might record an atmospheric glow or material illuminated by the blast. An increase 1 day later requires something that persists, travels, develops slowly, or changes the observing conditions after the detonation. The researchers discussed two broad possibilities. The first involved a previously unrecognized atmospheric or photographic effect. Nuclear radiation can interact with matter. Fallout can contaminate photographic material. Energetic particles can create marks in emulsions. Material lifted into the upper atmosphere might scatter or reflect sunlight. An explosion might affect the atmosphere in ways that produce unusual luminous events. The second possibility was far more speculative. The lights could represent reflective objects whose activity was somehow related to nuclear tests. This interpretation drew on the long-standing claim that unidentified aerial phenomena appear near nuclear activity. Under that scenario, an object in high orbit could produce a sunlight reflection on a Palomar plate. It might later descend, move into the atmosphere, or otherwise become visible to witnesses on the ground. The study did not demonstrate that sequence. No object was tracked from orbit to a reported sighting. No plate showed a point beginning in space, moving towards a nuclear test site and arriving at a known time. The comparison linked daily totals across different records. The suggested connection was based on timing, not on a measured path. A test could occur in the Soviet Union. A transient could be photographed in a completely different direction from Palomar, and a UFO could be reported in another country. When all three were recorded on the same date, they contributed to the statistical relationship, even when no direct geographic link had been shown. This use of worldwide dates increased the amount of available data, but it also weakened the physical interpretation. Time zones create another difficulty. A nuclear test listed on one calendar date in local time may occur on a different date at Palomar Observatory. A witness report may be entered according to the local time of the sighting. An astronomical exposure is usually recorded in universal time. Around midnight, one event can occupy two different calendar dates depending on the system being used. A 3-day test window reduces some of that problem because it includes the day before and the day after. The more specific finding that the strongest association occurred exactly 1 day after testing is more sensitive to time conversion and record accuracy. Historical test records are usually much better dated than UFO reports, but they are not all equally detailed. Witness databases may contain approximate dates, copied accounts, delayed reports, or cases whose times were reconstructed years later. The UFO data came from UFO-CAT, a large historical database developed from material associated with the University of Colorado's UFO study, and later maintained by the Center for UFO Studies. The researchers removed identical duplicate entries and retained only one report when several records described events on the same date in the same state. They then counted reports from separate states or countries as independent locations. This reduced obvious duplication, but it could not verify that every remaining report described a genuinely unexplained event. A bright planet may be reported by witnesses in several states. A meteor can cross a large region and generate many calls. A rocket launch, military exercise, balloon, aircraft formation, or widely publicized newspaper story can produce reports from different locations on the same evening. Two entries from separate states are not necessarily two unrelated objects. The authors acknowledged this problem. They stated that the UFCAT reports had not been systematically evaluated for validity, and that witness errors created substantial noise in the data. UFO reports were also extremely common in the dataset. At least one report existed on 2,428 of the 2,718 dates, or about 89.3% of the full period. Because almost every day contained a report, simply comparing days with UFOs against days without them was not very informative. The study found no significant relationship when both variables were treated only as yes or no categories. The researchers therefore examined the number of reports. Among the 310 dates on which at least one transient was recorded, the correlation between the number of transients and the number of independent UFO reports was positive but small. The reported Spearman correlation was 0.138, with a probability value of 0.015. A correlation of 0.138 is weak. It indicates a slight tendency for dates with more reported UFOs to contain more transient candidates, but the two quantities do not rise together in a close or predictable way. Many dates with reports had few or no transients. Some dates with numerous transients had no exceptional wave of sightings. A second statistical model used all 2,718 dates and accounted for the highly uneven transient counts, with a negative binomial distribution. In that model, each additional UFO report on a date was associated with an 8.5% increase in the expected transient count. This result also sounds stronger when removed from its setting. One additional report was associated with an 8.5% increase in the model's expected count. It did not mean that each witness caused another set of lights to appear. It did not establish that the witnesses and telescopes saw the same object. The analysis showed a relationship between daily totals after a particular statistical method had been applied. Bruel and Villarroel also combined the two predictors. Dates with neither a UFO report nor a nuclear test window contained the lowest expected transient counts. Dates with either a UFO report or a nuclear test window contained more. Dates containing both had the highest fitted counts. The authors described the pattern as potentially additive. Nuclear testing windows also contained slightly more UFO reports than other dates. That result agreed with the general idea that unusual aerial reports increased around nuclear activity, although it did not identify the source of those reports. Several ordinary mechanisms could produce such an association. A nuclear test involved military aircraft, tracking stations, balloons, communications equipment, security operations, scientific instruments, and public concern. Some of those activities could create unusual sights. People near a test region might pay closer attention to the sky. Newspapers reporting nuclear events could increase public anxiety and encourage more people to report ordinary objects. Tests could also coincide with periods of broader military activity. A government preparing to detonate a weapon might launch weather balloons, reconnaissance aircraft, sampling systems, or rockets. Those devices could create both photographic flashes and witness reports without requiring anything non-human. Atmospheric effects remain possible as well. Above-ground explosions lifted dust and radioactive material into the atmosphere. High-altitude debris might remain illuminated after sunset. Charged particles could interact with the upper atmosphere or photographic material. A point-like appearance would need to be explained because a diffuse cloud or continuously moving object should normally create a patch or trail rather than a compact point during a long exposure. A very brief reflection from a small piece of material could produce a point. The question would then become whether nuclear tests could place reflective debris high enough, keep it there long enough, and position it within Palomar's fields often enough to generate the measured increase. Debris lifted by a nuclear explosion would not enter stable geosynchronous orbit. The energy and direction required for orbit are far beyond what random fragments would receive from an atmospheric detonation. Material could reach high altitudes without remaining there permanently, but it would follow ballistic or atmospheric paths. If the transients were genuinely in distant Earth orbit, nuclear debris would not provide a simple explanation. Contamination of the plates offers another route. Radioactive particles can fog photographic film. During the middle of the 20th century, manufacturers learned that fallout and contaminated packaging could damage sensitive photographic materials. A radioactive particle striking an emulsion may create a local mark. Bruel and Villarroel argued that fallout contamination would tend to produce diffuse fogging rather than the compact star-like profiles of the reported transients. They also noted that contamination at Palomar would not easily explain a relationship with UFO reports made in distant locations. That objection assumes that the UFO correlation is independent and reliable. When two noisy datasets are linked to the same dates, a third factor can influence both. The Palomar observing schedule is one of the most important possibilities. A transient could be detected only on a night when the telescope exposed plates. More plates created more opportunities to find marks. Long observing runs could produce large daily counts. Weather, moon phase, season, maintenance, and survey planning determined when the telescope operated and how much sky it covered. Nuclear tests were not distributed evenly through the years either. They occurred in campaigns and series. UFO reports also rose and fell with public interest, military activity, major news stories, and famous incidents. When several records contain strong trends and clusters in time, an apparent correlation can emerge because they all change across the same years or seasons. A 2026 critical preprint led by Wesley Waters argued that the reported nuclear test relationship became statistically insignificant after the transient counts were normalized by the number of Palomar observation days. The authors said the association was almost entirely determined by the telescope's observing schedule. They also questioned whether the large transient catalogue had been sufficiently validated, noting that it contained catalogue stars, scanning artifacts, and plate defects. Villarroel, Bruel, and collaborators disputed that assessment. They argued that the critics used a much smaller dataset created for another purpose, that the reduced sample lacked complete timing information, and that it was too small to test the reported population patterns properly. They also raised concerns about how plates and exposure times had been assigned in the critical analysis. This disagreement is not a minor technical detail. Suppose Palomar operated on only a small number of nights near nuclear tests, but took many plates on those nights. A comparison based only on whether any transient appeared during the date may treat each busy observing night like an ordinary day. A count-based model may then reflect the number and quality of plates rather than a change in the sky. A robust analysis should account for exposure time, number of plates, sky area covered, plate sensitivity, weather, and the number of usable fields recorded on each date. The original study used daily transient totals but did not model all of those observing variables directly. Its authors presented the work as a preliminary test and acknowledged significant noise in both the photographic and witness datasets. Later researchers attempted to reproduce parts of the result. A 2026 preprint by Brian Doherty reported that the original 45% relative risk result could be reproduced from the published dataset. That analysis also used negative binomial regression with controls for precipitation, cloud cover, and lunar illumination, and reported that the nuclear relationship remained. A permutation test found that the timing association was unlikely under random rearrangement of the test dates. This is useful, but it is important to understand what was independently reproduced. The calculations were repeated by a different researcher. The underlying transient catalogue, nuclear test list and historical plates were not independently recreated from the beginning. Any contamination or selection bias already present in the original transient data would remain. An independent analysis of the same numbers can confirm that the arithmetic is reproducible. It cannot by itself prove that each input represents a real event in the sky. Another 2026 preprint examined geomagnetic activity and reported that transient detection rates declined during stronger geomagnetic storms. Its author argued that controlling for geomagnetic conditions strengthened the nuclear association. That result is recent, has not settled the disagreement, and again relies on the same broad archival dataset. The historical UFO connection also gained attention because of two dates in July 1952. On July 19th and July 27th, multiple bright transient candidates appeared in Palomar images. Those dates matched 2 weekends during the famous Washington, D.C. UFO reports, when unusual radar returns and visual sightings were reported around the American capital. Villarroel and Villarroel presented this overlap as a motivating example for their broader statistical comparison. The overlap is memorable, but it does not establish that the Palomar lights were the Washington objects. Palomar Observatory is in California. The telescope was photographing selected astronomical fields rather than watching the airspace above Washington. The triple transient recorded on July 19th appeared in one small region of the celestial sky and vanished before a following exposure. There is no measured trajectory connecting those points with the radar reports. The two records share dates. That is interesting enough to investigate, but a date alone cannot provide distance, identity, or motion. The 1952 period also contained an exceptionally high level of public UFO attention. Reports encouraged more reports. Newspaper coverage led more people to watch the sky. Radar operators, pilots, military personnel, and civilians were alert to unusual activity. Temperature inversions, ordinary aircraft, meteors, stars, and misinterpretations have all been proposed for parts of the Washington incidents, while some details remain debated. A large wave of reports increases the chance that an unrelated Palomar exposure will share a date with one of them. The statistical study was meant to move beyond one dramatic coincidence by using the full 7.5-year period. That was the correct direction. A broad comparison is better than selecting only famous nights. The broad comparison still inherits the weaknesses of its source records. The transient catalogue may contain defects. The UFO database contains unverified sightings. Nuclear tests occurred in clusters. Palomar observations were uneven. Dates may cross time zones. The number of statistical comparisons matters. The 3-day nuclear window was chosen in advance, which is preferable to choosing it after seeing the result. The individual day-by-day tests were secondary and post hoc. When several time offsets are tested, the probability that one appears significant by chance increases unless the analysis corrects for the number of comparisons. The fact that only the following day reached significance is therefore suggestive, but it should not be treated as an established 24-hour response. A physical explanation would also need to account for a curious historical change reported in the paper. The last transient found inside a nuclear test window occurred on March 17, 1956, even though another 38 above-ground tests took place during the remaining 13 months covered by the dataset. The authors compared this decline with claims that UFO reports near nuclear production facilities also decreased sharply during the middle of the 1950s. They suggested that the parallel change might be meaningful, while acknowledging that its cause was unclear. It could indicate a change in an unknown phenomenon. It could also reflect changes in the survey schedule, plate quality, source filtering, test locations, observation seasons, public reporting, or the construction of the underlying database. When a proposed effect stops while its supposed trigger continues, the explanation needs another variable. The nuclear and UFO patterns therefore do not convert the Palomar marks into confirmed machines. They provide correlations that may guide further testing. The strongest interpretation would require several claims to be correct at once. The points must be genuine optical events. A meaningful fraction must come from objects near Earth. The objects must be reflective or self-luminous. Their activity must change around nuclear tests. The UFO reports must be linked to the same population. Known military, atmospheric, photographic, and statistical effects must fail to explain the relationship. At present, none of those steps has been fully established. The results remain interesting because different records created for different reasons appear to show small relationships. Palomar plates, nuclear test dates, and historical witness accounts were not originally assembled to support one another. Finding a pattern among them deserves scrutiny. Small correlations in large and noisy historical datasets are also easy to overinterpret. The correct response is neither to announce that visitors monitored Cold War weapons tests, nor to dismiss the entire exercise because UFO reports were included. The useful response is to ask whether the patterns survive improved controls, cleaner candidate lists, independent plate archives, accurate time conversion, and models that include the telescope's actual observing schedule. There is a much less dramatic explanation for the Palomar lights, and it begins without spacecraft, secret observers, or anything moving through the sky at all. It begins with damaged photography. That possibility may not be as exciting as reflective objects near Earth, but it has one major advantage. Old photographic plates are known to develop marks that can resemble astronomical sources. The plates were exposed, chemically developed, handled, copied, transported, stored, scanned, and processed by software. A problem introduced during any one of those stages could leave behind a small point that later looked like a vanished star. For critics of the VASCO interpretation, this is not a minor alternative placed at the bottom of a long list. It is the explanation that should be considered first. A point on a photographic plate is only useful as evidence of something in the sky when researchers can show that light entered the telescope and produced it. Until that step is secure, every discussion of distance, orbit, sunlight, and possible technology rests on an uncertain foundation. This is especially important for the first Palomar survey because many researchers do not work directly from the original photographic negatives. They use digitized versions created from glass copies. Those copies were made so astronomical institutions could obtain their own versions of the survey without borrowing Palomar's original plates. A physical copy does not behave like a duplicated computer file. To reproduce a photographic plate, technicians could make a positive image from the original negative and then use that positive to create another negative copy. The final glass plate contained the astronomical field, but it could also inherit any flaw introduced during the intermediate stages. A speck of dust placed between two surfaces might create a mark. A small hole in the emulsion of a positive could become a dark point in the copied negative. A bubble could disturb the coating. The glass could be scratched. Pressure from handling could damage a small area. Chemicals might develop unevenly. A static discharge could expose part of the emulsion. The final mark might be compact enough to resemble a faint star, particularly after the plate was scanned and the surrounding background was processed by detection software. This creates a problem for one of the checks that initially seemed reassuring. Some candidate transients appeared in more than one digital scan of the Palomar material. At first, this appeared to show that a scanner had not invented them. Two scanning systems, working separately, recorded the same points. That conclusion is partly correct. When the same mark appears in two scans, a one-time electronic error in one scanner becomes unlikely. However, if both scanned glass plates were copied from the same intermediate photographic material, they may have inherited the same physical defect before either scanner was involved. Two scans can therefore be independent at the digital stage while remaining dependent at the photographic stage. The difference is rather like finding the same spelling mistake in two printed books. It may prove that neither reader imagined the mistake. It does not prove that the mistake was present in the author's original manuscript. Both books may have been printed from the same faulty typesetting. Nicholas Hambley and Andrew Blair examine this issue directly in a 2024 analysis of the apparent Palomar transients. They studied glass copy plates held at the Royal Observatory in Edinburgh and used measurements from the Supercosmos Sky Survey to compare the shapes of ordinary astronomical sources with the disputed marks. They concluded that the famous transient candidates were likely to be spurious artefacts associated with the photographic emulsion or the plate copying process. Their inspection confirmed something important. The candidate points were physically present on the glass copies. They were not simply false pixels introduced when a modern scanner converted the plate into a digital image. That sounds helpful to the transient case, but Hambley and Blair also saw other physical defects in the photographic material. They described blemishes such as bubbles and holes in the emulsion. Some of those defects could produce compact detections after copying and scanning. In their proposed explanation, a tiny hole in an intermediate positive would allow light to pass through during the production of a negative copy. The resulting copy could contain a small dark image. Because stars also appear as dark points on a negative photographic plate, the defect might resemble a real astronomical source. Its brightness profile could even appear reasonably smooth. This is one reason visual inspection does not always settle the question. A person may reject an obvious scratch, stain, or irregular patch. A small circular defect is more difficult. The eye sees something shaped like a star and naturally begins treating it as one. Hambley and Blair attempted to move beyond visual judgment by measuring source morphology. A real star on a long exposure has a characteristic profile. Its brightness is strongest near the centre and falls towards the edges. Atmospheric turbulence, telescope focus, tracking accuracy, and the photographic response all influence the exact shape. Galaxies tend to look broader. Scratches and stains often appear elongated or irregular. The researchers used several measured properties to train a random forest classifier. This is a machine learning method that combines many decision trees. Each tree examines features such as width, roundness, concentration, or ellipticity, and the combined system assigns the source to a likely category. When they applied this method to the 9 famous points from the April 1950 plate, all 9 were classified as likely bad or spurious detections rather than ordinary stellar images. Hambley and Blair argued that the marks were narrower and rounder than the normal stars surrounding them. At first, that appears damaging to the glint hypothesis. When a mark does not resemble the stars on the same exposure, a photographic defect seems reasonable. Villarroel and her colleagues offered the opposite interpretation. A star shines throughout most or all of the exposure. During that time, atmospheric seeing and small tracking changes spread its light across a wider area. A glint lasting less than a second is recorded only briefly. It experiences much less blurring and could therefore produce a point that is sharper and more circular than a star. From this perspective, the unusual profiles found by Hambley and Blair are not signs that the marks were created in the emulsion. They are what short optical flashes should look like on a long photographic exposure. Villarroel, Enrique Solano, and Geoffrey Marcy later argued that sub-second flashes should naturally appear narrower than continuously exposed stars, and that the profile analysis was therefore consistent with the transient interpretation rather than a refutation of it. The same measurement now supports 2 explanations. The marks are unusually sharp. Critics say they are too sharp to be astronomical sources. Supporters say they are sharp because the astronomical events were unusually brief. This is where a laboratory experiment would be more useful than another exchange of interpretations. Researchers could obtain photographic material resembling the plates used in the early Palomar survey. They could record ordinary stars during long exposures and introduce controlled flashes lasting 1 second, 1/10 of a second, and 1/100th of a second. They could then compare those profiles with marks created by dust, pinholes, bubbles, scratches, static discharges, chemical droplets, and copying defects. The test would not need to involve alien technology. A lamp, mirror, rotating shutter, and careful photographic setup would be enough. When real flashes and real defects were produced under known conditions, the Palomar points could be compared with both groups. At present, the argument often relies on what each process is expected to look like, rather than on a complete historical reconstruction using comparable materials. Even a successful experiment would have limits. The original plates were manufactured and processed many decades ago. Their emulsions aged. Storage conditions differed. Copying equipment left its own effects. Modern photographic material may not reproduce every property of the historical glass. It would still provide a better reference than intuition alone. Another weakness concerns the use of automated catalogues. Software designed to find stars must decide where the background ends and a source begins. It looks for groups of pixels that rise above a selected brightness threshold. It then measures their shapes and assigns positions and magnitudes. When the plate contains millions of real stars and thousands of defects, even a highly accurate program can produce a large number of mistakes. Suppose a detection system correctly rejects 99.9% of false marks. That sounds excellent. When it examines several million imperfections, the remaining 0.1% can still create thousands of candidates. The size of a catalogue does not prove that the sky produced all of its entries. It may prove that the search covered a very large amount of photographic material. The filtering rules used by VASCO removed many obvious problems. Candidate detections were compared with modern catalogues. Known asteroids, variables, moving stars, diffraction spikes, elongated marks, and sources with infrared counterparts were excluded where possible. The published work reduced hundreds of thousands of preliminary unmatched detections to much smaller samples, including 5,399 unidentified candidates in one carefully described catalogue. No filter is perfect. A genuine event can be removed because it looks slightly unusual. A defect can remain because it looks unusually convincing. The balance between these errors changes depending on how strict the rules are. Loose filtering preserves more possible transients, but it also preserves more contamination. Strict filtering creates a cleaner sample, but it may remove the rare events the project is trying to find. There is no single setting marked "remove every defect" while retaining every alien spacecraft. Astronomy software remains disappointingly unwilling to provide that option. The broad dataset used for some of the statistical claims creates additional concern. The sample of more than 100,000 unidentified features was not individually confirmed as a collection of real optical events. It included detection selected through catalogue matching and automatic criteria, but large-scale visual or physical validation was incomplete. Watters and his collaborators argued in a 2026 critical analysis that the datasets contained catalogue stars, scanning artifacts, and plate defects. They reported that many unidentified features became more common towards plate corners and edges. They also found empty strips, geometric clusters, voids, and irregular concentrations that appeared more consistent with instrumental or processing effects than with objects distributed across the sky. This spatial pattern matters. A population of distant astronomical sources should usually follow astronomical structures. Stars become denser near the Milky Way. Galaxies become harder to identify in crowded regions. Asteroids remain near the plane of the solar system. Nearby artificial objects might follow orbital bands or illumination geometry. Photographic defects follow the plate. They may increase near edges where handling and optical distortion are worse. They may form strips corresponding to scanning paths. They may collect in damaged regions. They may avoid areas where software fails to extract sources. Their distribution can have straight boundaries, repeated shapes, and abrupt changes that do not belong to the sky. When suspicious detections align with the physical geometry of a photographic plate, the case for instrumental contamination becomes stronger. The challenge is that real source detection is also affected by plate geometry. The edges of a Schmidt plate can have poorer focus, greater distortion, different sensitivity, and stronger vignetting. Real stars near the edge may be measured less reliably. Catalogue matching may fail more frequently there. A rise in unidentified sources towards the corners can therefore be caused by several related effects, not only literal scratches or holes. From the point of view of the alien interpretation, the exact cause makes little difference. When the plate itself explains where candidates appear, the claim that they represent nearby objects becomes less secure. Plate-to-plate variation produces another warning. Some Palomar exposures contain very few unmatched sources. Others contain hundreds or thousands. A genuine transient population could vary with observing conditions and sky position, but extreme differences may indicate that certain plates are unusually damaged or poorly processed. One bad plate can contribute a large fraction of a statistical signal. Imagine surveying several towns for unusual birds. Most observers report one or two. One observer reports 4,000 from a kitchen window, but has accidentally counted marks on the glass. A calculation based on the full total may reveal a very exciting migration that exists mainly in need of window cleaner. Researchers must therefore analyse the plates individually. How many candidates came from each exposure? Did the strongest results remain after plates with extreme counts were removed? Were particular plate series, dates, copying generations, or scanning systems responsible for most of the events? Did the shadow deficit exist across many plates, or was it driven by a small subset? Did the nuclear test relationship remain when the amount of sky photographed each night was included? These questions move the investigation from interesting correlations towards data quality. The famous groups of multiple transients require the same treatment. 9 marks within a small region appear unlikely when each mark is assumed to occur independently and randomly. Plate damage is not necessarily independent or random. A local chemical problem can create several points in one patch. Dust can cluster. A damaged copying surface can leave neighbouring holes. Pressure or contact may affect a limited area. Straight alignments can also have instrumental causes. Scratches are straight. Scanning errors can follow rows or columns. Diffraction spikes extend along preferred directions. Plate copying can create repeated structures. Software can break one irregular feature into several separate point detections arranged along a line. A statistical calculation that compares an observed alignment with random dots may assign it a very low probability. That result is relevant only when random dots are the correct model for the background. When the background contains scratches and geometric artifacts, straight arrangements are exactly what one might expect. This does not prove that every alignment is defective. It shows that the null hypothesis must resemble real photographic damage, not an ideal field of evenly scattered points. The 2026 critique led by Waters reported that roughly 1/3 of the features included in the claimed linear clusters had not been confidently separated from known catalogue stars. The authors said that, after applying their more vetted dataset, they did not reproduce the reported Earth shadow deficit, and found that the nuclear test association weakened after accounting for the Palomar observing schedule. Villarroel, Alina Streblianska, Stephen Bruil, and Stefan Geyer responded that the critical team had used a much smaller and differently constructed subset. They argued that it was created for another purpose, lacked complete temporal information, and did not contain enough events to test the ensemble statistics properly. They also questioned aspects of the plate assignment and coordinate calculations used in the reanalysis. The disagreement reveals 2 separate standards of evidence. Critics want each candidate or a large representative sample to be shown convincingly to be a real optical event before population statistics are interpreted. The VASCO researchers argue that an ensemble can contain many false detections and still reveal a physical subpopulation through statistical behaviour. Under that view, object-by-object certainty is helpful but not required when the contaminants should be unrelated to Earth's shadow, UFO dates, or nuclear tests. Both positions are defensible in some circumstances. Astronomers often detect populations statistically before identifying every member. Weak gravitational lensing, background radiation, and faint galaxy surveys all rely on signals that emerge from noisy samples. That approach works only when the noise is understood well enough. When contamination varies with plate location, observation date, scanning method, survey schedule, and source selection rules, it may not behave randomly. The noise can create patterns of its own. A defect does not respond to Earth's shadow. The number of detected defects can still correlate with the shadow when the telescope observes different plate regions at different dates. A scratch does not respond to a nuclear test. The catalogue can still show more scratches near test dates, when Palomar took more plates during those periods. Dust does not generate UFO reports. Military activity, public attention, seasonal observing, and changing data quality can influence both datasets without any dust particle receiving a newspaper subscription. This is the central skeptical case. No critic needs to prove the origin of every mark. The claim of nearby artificial objects becomes weak when ordinary imperfections have not been excluded, and when the reported patterns may depend on how uncertain detections were selected. The burden is especially high because the final interpretation is extraordinary. A new class of rare stellar flare requires good evidence. An unknown atmospheric effect requires stronger evidence. Reflective non-human technology orbiting Earth before Sputnik requires evidence that survives every reasonable test of plates, copies, catalogues, timing, geometry, and statistics. The original 2021 study of the 9 simultaneous candidates was cautious on this point. Its authors included unknown contamination as a possible explanation, and stated that solar reflections from objects near geosynchronous orbit should be considered only when contamination could be fully excluded. Contamination has not been fully excluded. That is not the same as saying contamination has been proved. Hambley and Blair proposed a plausible copying mechanism and showed that the source profiles differed from normal stellar images. They did not locate the exact intermediate positive containing the precise holes responsible for every candidate. They could not rewind the copying process and watch the marks being formed. Watters and colleagues identified catalogue problems and spatial patterns suggestive of artifacts. Their work appeared as a recent preprint and was challenged by the original researchers. The discussion remains active rather than settled. A complete rejection of the mystery would require its own positive evidence. Researchers would ideally inspect the original Palomar negatives under a microscope. When the marks appeared only on later copies, the copying explanation would become extremely strong. When they appeared on the original negatives, a later copying defect would be ruled out, although original plate contamination would remain possible. Independent plates taken at nearly the same time would be even better. A defect created at Palomar should not appear at the same celestial coordinate on an original plate exposed by another observatory. A genuine flash could. The old archives may contain such comparisons, but finding them is difficult. The second observatory would need to have photographed the right field during the short period when the source was visible. Its plate would need sufficient sensitivity. Its records would need accurate timing. The material would need to survive and be available for scanning or inspection. Most candidate flashes may never receive that kind of confirmation. Modern experiments can still test the process. Researchers can recreate plate defects, copying flaws and sub-second reflections. Machine classifiers can be trained on controlled examples instead of labels assigned only from the historical images. Blind analyses can prevent teams from knowing which marks come from claimed transient fields until the classification is complete. Different groups can begin with the same raw scans and publish complete selection pipelines. Every rejected and accepted source can be made available. Results can be repeated with different thresholds. Plate edges can be tested separately from centers. Extreme plates can be removed one at a time. Known stars can be inserted to measure recovery rates. Artificial defects can be added to determine how often they survive filtering. The investigation becomes less glamorous as these controls accumulate. It also becomes more reliable. Perhaps the most useful attitude is to treat the marks neither as spacecraft nor as meaningless dirt. They are unresolved data quality problems with possible astronomical content. Some may be ordinary stars missed by catalogue matching. Some may be flares or other genuine transients. Some may be asteroids. Some may be plate defects. Some may be reflections from balloons, aircraft, or experimental equipment. A small remainder may resist every available explanation. Placing all of them into one category creates unnecessary confusion. The catalogue probably contains a mixture, and the difficult task is to estimate how much of each ingredient is present. Dust and defects therefore make a strong case against declaring the mystery solved in favour of alien technology. They do not make further investigation pointless. They identify the controls that any future claim must pass. By the time every ordinary possibility is placed beside the Palomar plates, the mystery no longer looks like a simple contest between aliens and damaged glass. A more realistic explanation may involve several earthly causes working together, with each one accounting for a different part of the data. Some marks may be photographic defects, some may be ordinary stars that were matched incorrectly. Others may be real flashes caused by balloons, aircraft, rockets, meteors, or reflective material in the upper atmosphere. A statistical pattern could then emerge from the way the telescope operated, rather than from one unusual population of objects. That kind of mixed explanation is not as satisfying as identifying one clear cause. Science is under no obligation to provide a tidy answer, particularly when the evidence consists of thousands of marks collected over several years by equipment that was never designed to investigate them. Balloons deserve special attention, because they were already common in the period before Sputnik. During the late 1940s and 1950s, the United States operated large balloon programs for scientific and military purposes. Project Mogul used balloon trains carrying instruments intended to detect distant nuclear tests. Other programs studied cosmic rays, atmospheric conditions, photography, human survival at high altitude, and long-distance reconnaissance. The Navy's Stratolab program began in the middle of the 1950s and used plastic balloons as high-altitude laboratories, while later manned systems demonstrated that enormous balloons could remain aloft for long periods, with substantial equipment suspended beneath them. A high-altitude balloon can look very different depending on where the observer stands and where the sun is located. During daylight, the balloon envelope may appear pale or nearly transparent. At night, the entire system may be invisible. Shortly after sunset, the observer can be standing in darkness while the balloon remains illuminated at altitude. A smooth section of material, a metal instrument box, a camera housing, or part of this suspension equipment may briefly send sunlight towards a telescope. The resulting reflection could be bright and short. A balloon does not need to switch on a lamp. It needs only to rotate, twist, or change its orientation in the wind. The reflective angle may be correct for a fraction of a second and then disappear. During a 50-minute photographic exposure, a continuous light moving across the field should create a trail. A reflection lasting only a fraction of a second can leave a compact point. The plate records the position where the flash occurred, but does not show the balloon before or after the reflection. That makes balloons a plausible explanation for individual Palomar points. Several details must still fit. A balloon is close to Earth compared with an orbiting object. Because it is nearby, even slow physical movement can produce noticeable movement against the stars. The glint must be short enough that this motion does not spread the image. Its brightness must be sufficient to register through the long exposure. The balloon must also occupy the small region of sky covered by the plate at the correct time. None of those requirements is impossible. The difficulty comes when balloons are asked to explain the whole reported population. Balloon paths are controlled largely by winds. Launches occur from particular sites. Flights remain within the atmosphere and have limited durations. Their distribution should be related to weather, military ranges, recovery regions, and known balloon campaigns. A large sample caused by balloons should contain patterns reflecting those conditions. The Earth's shadow result also creates a problem. An object at balloon altitude enters darkness under different circumstances from an object near geosynchronous orbit. It cannot remain sunlit as far into the night because it is only a few tens of kilometers above the surface. A shadow calculation based on an altitude of roughly 36,000 kilometers cannot be applied directly to a balloon. A candidate classified as illuminated at geosynchronous distance might already be in darkness if it were a balloon. A point classified inside the distant orbital shadow could have a different illumination status at atmospheric altitude. This means the reported shortage inside Earth's shadow supports balloons only weakly unless the calculation is repeated across realistic balloon altitudes. Researchers could perform that test. For every plate, they could calculate illumination at 10, 20, 30, and 40 kilometers above Earth. They could include the actual position of Palomar, the sun's altitude, atmospheric refraction, and possible balloon routes. When the strongest deficit consistently appeared at an altitude associated with balloons, the atmospheric explanation would gain support. When it appeared only near geosynchronous distance, balloons would become less convincing. Distance cannot be extracted directly from a single photographic point, so the shadow pattern is one of the few available indirect clues. It must therefore be modelled carefully rather than treated as a simple light switch. Military aircraft create a similar mixture of possibility and limitation. California and the American Southwest contained major flight test activity during the Palomar survey years. Rocket aircraft and high-altitude research planes were pushing speed and altitude records. In 1951, the D-5582 skyrocket reached almost 80,000 feet, and experimental aviation continued advancing throughout the decade. A polished aircraft surface can reflect sunlight. Navigation lights can flash. Exhaust may glow. Experimental equipment can produce unusual appearances. A plane travelling nearly towards or away from the telescope may show less sideways motion than one crossing the field. Aircraft usually create trails in long exposures, especially when their lights remain visible. A single short reflection can still appear point-like. Several flashes could form a broken line. This offers an ordinary explanation for some isolated points and alignments. It does not automatically explain sources spread across widely separated astronomical fields or a population that follows distant orbital shadow geometry. Aircraft would also be constrained by routes, altitude, fuel, weather, and the location of military facilities. The same reasoning applies to rockets. Sounding rockets existed before Sputnik and could carry instruments above most of the atmosphere. Their engines, exhaust clouds, separated components, and tumbling debris might produce short-lived lights. A rocket rises and falls quickly. It does not remain at geosynchronous distance. Its motion should often create a trail unless the flash is very short or the path is aligned favourably with the telescope. Known launches can be checked against plate dates, although secret programs and incomplete records prevent perfect reconstruction. A few candidates may well come from balloons, aircraft, or rockets. The claim becomes more difficult only when one earthly explanation is expected to account for every point, every cluster, the Earth shadow deficit, the UFO correlation, and the nuclear test association at the same time. No rule requires that. A catalogue assembled from old photographic material is likely to be heterogeneous. One plate may contain a scratch, another may record an asteroid, a third may catch a balloon glint, a real stellar flare may survive alongside all three. A later analysis can mistakenly treat them as one population, because they share only one property. They appear in an old image and lack an obvious modern counterpart. Solar and geomagnetic activity add another possible source of variation. Energetic particles can interact with photographic material. Space weather changes Earth's upper atmosphere and magnetic environment. It can influence auroral activity, radio communication, high-altitude electrical conditions, and the behavior of charged dust or particles. A recent preprint proposed that the Palomar transient rate may change around geomagnetic storms and suggested a mechanism involving charged dust near geosynchronous distance. That work is preliminary, depends on the same disputed archival data, and requires independent confirmation. It is useful, mainly because it demonstrates that a real non-technological phenomenon near Earth could, in principle, create a sunlight-dependent signal without involving balloons or alien machines. Reflective dust is not an easy answer either. Individual dust grains are normally too small and faint to create the reported points. A compact group or larger fragment would need the correct size, reflectivity, orientation, and lifetime. The mechanism would need to explain why the events appeared during the Palomar period, why they formed occasional clusters, and why similar detections have not been established through independent archives. Still, natural material near Earth occupies the wide space between photographic defect and constructed spacecraft. That space includes meteoroid fragments, ice particles, dust clouds, material released by rockets, atmospheric debris, and physical processes not recognized when the plates were taken. The statistical questions are more serious than any one proposed object. The daily data set used in the nuclear and UFO study covered 2,718 days. Candidate transients appeared on 310 of them. A single date could contain no detections or as many as 4,528, partly because the number of plates and fields observed varied. The distribution was extremely uneven. When data behave like this, the average can be misleading. Imagine a cafe that sells 10 cups of tea on most days and 4,000 cups during one festival. The ordinary daily average may rise dramatically, even though nothing changed on most dates. Any event coinciding with the festival can appear connected with tea consumption. Palomar had its own version of busy and quiet days. Some nights produced multiple usable plates, others produced none. Weather could close the telescope, bright moonlight could limit observations, maintenance, survey priorities, seasons, and the position of each target affected the schedule. A transient could be found only when a plate existed. More plates meant more opportunities to detect real flashes, ordinary stars, scratches, dust, and copying defects. A date containing 10 plates should not necessarily be compared with a date containing none, as though both offered equal chances of discovering a transient. This is the basis of the scheduling bias criticism. The 2025 study reported that transients were 45% more likely on dates within 1 day of an above-ground nuclear test. It also reported a weak positive correlation between the number of candidates and the number of UFO reports, with a Spearman correlation of 0.138. A count model associated each additional UFO report with an 8.5% increase in the expected number of transients. The authors described the results as preliminary associations rather than proof of causation. Each result asks a different question. The 45% figure compares the proportion of test window dates containing at least one transient with the proportion outside those windows. The correlation of 0.138 measures a weak tendency for two daily counts to rise together. The 8.5% value comes from a statistical model designed for over-dispersed count data. None measures the probability that a transient was a UFO. None identifies which object, witness report, or nuclear test produced a particular mark. None establishes a physical path connecting a test site, an object near Earth, and Palomar Observatory. The calculations can be correct while the interpretation remains uncertain. A probability value such as 0.008 asks how unusual the observed difference would be under a specified null model. It does not ask whether balloons, aliens, defects, or telescope scheduling are most likely. That comparison requires separate physical and statistical evidence. The null model may also be incomplete. When neighbouring dates are correlated, observations are uneven, tests occur in campaigns, and transient counts are dominated by a few extreme nights, a simple comparison of calendar days may assign too much significance to the pattern. Nuclear tests were not spread randomly across the period. They occurred in organised series. Military activity and public attention clustered around them. UFO reports also changed over time, partly because major stories encouraged people to watch the sky and submit reports. Palomar's work followed its own schedule. When several time series contain clusters, trends, and seasonal changes, they can overlap without sharing a direct cause. A useful test would shuffle test dates while preserving their clustering and seasonal structure. Another would compare the transient rate per usable plate, or per hour of exposure, rather than per calendar day. Researchers could also include the number of plates, sky area, limiting magnitude, weather, moon illumination, and plate quality in the model. A 2026 critique led by Wesley Waters argued that the nuclear test relationship became statistically insignificant after normalizing for Palomar observation days. The same paper reported that the more heavily vetted transient sample did not reproduce the Earth shadow deficit, and that many features followed plate edges, geometric structures, or known catalogue sources. The authors concluded that none of the disputed features had yet been demonstrated to be genuine optical transients. Villarroel and her collaborators responded that the critical analysis relied on a sample, reduced by roughly a factor of 20, and originally created for another purpose. They argued that it lacked complete timing information, was underpowered for the Earth shadow test, and may have assigned plate times incorrectly. They maintained that the original statistical findings had not been invalidated. The disagreement cannot be resolved by comparing the confidence of the two groups. Both sides raise valid concerns. The critics are correct that an unvalidated catalogue can produce misleading statistics. When the sample contains stars, defects, scanner artifacts, and uncertain plate assignments, a strong numerical result may reflect data construction rather than a new phenomenon. The VASCO team is correct that aggressive filtering can remove a genuine minority population along with the contamination. A result can disappear because the sample became too small, not because the original effect was false. Suppose one object in every 100 is a real glint. A sample of 100,000 detections could contain about 1,000 glints, enough to reveal a population pattern even when many individual marks are uncertain. Reduce the sample to 5,000 using a filter that accidentally removes most unusually sharp sources, and the glint signal may vanish. The cleaner-looking sample may be less useful for the exact question being asked. The solution is not to choose the large dirty catalogue or the small uncertain one. The solution is to create a large, independently validated catalogue with complete observing information. Every candidate should be linked to the correct original plate, exposure time, field position, copying history, and modern counterpart search. Plate centres and edges should be analysed separately. Extreme plates should be tested one at a time. The statistical plan should be written before the final sample is examined. Several comparison groups would help. Known stars could show how genuine sources behave across each plate. Known defects could show how contamination changes near edges and damaged regions. Modern satellite glints could be inserted into simulated historical exposures. Artificial short flashes could be recorded on comparable photographic material. Balloons and aircraft could be modelled at realistic heights. Earth's shadow could be calculated across a wide range of distances rather than at one preferred orbit. The nuclear analysis should use exposure opportunity as its basic unit. A night with 6 hours of usable imaging should carry more information than a cloudy date with no plates. UFO reports should be corrected for duplicate events, media waves, meteors, launches, and changes in reporting systems where possible. Even a perfect statistical analysis would not identify aliens by itself. Statistics can show that a population behaves differently from no noise. Physical observations are needed to determine what the population is. That is why an independent photographic archive matters so much. When another observatory recorded a similar Earth shadow deficit using original plates made with different equipment and processed through a different laboratory, local Palomar explanations would weaken. When two observatories captured the same brief source at the same celestial position and time, a plate defect would become extremely unlikely. The slight difference in apparent position between the sites could reveal distance through parallax. A nearby atmospheric object would shift more than an object near geosynchronous orbit. A distant star would show almost no shift. The old Palomar points rarely offer that opportunity. Modern instruments do. A network of rapid cameras could watch inside and outside Earth's shadow simultaneously. Each event could be timed to a fraction of a second. Its motion, colour, polarization, brightness pattern, and parallax could be measured. Radar and satellite catalogues could identify ordinary spacecraft. Balloons and aircraft could be tracked. Unmatched events could trigger immediate observations from larger telescopes. Such a survey would directly test the phenomenon, rather than infer it from marks discovered decades later. Earthly causes can explain many features of the current evidence. Balloons can produce brief reflections. Aircraft and rockets can create moving lights. Photographic defects can imitate stars. Catalogue matching can create false disappearances. Telescope schedules can distort daily statistics. Public attention can alter UFO report counts. Solar and geomagnetic conditions may change the near-Earth environment. None has yet been shown to explain every claimed pattern on its own. That may be because the patterns share no single cause. A mixture of defects, natural events, human technology, and statistical bias is less dramatic than a hidden orbital presence, but it currently requires fewer unsupported assumptions. The remaining unexplained portion may become smaller as the data improve, or it may become more distinct. Only then can the final question be answered fairly. Are these marks the strongest evidence yet that non-human technology was present near Earth, or are they an unfinished investigation whose most important evidence has not been collected? Calling any observation our strongest evidence of aliens creates an immediate problem. The phrase sounds as though scientists have reached a shared conclusion and are now deciding where to park the welcome committee. They have not. The Palomar findings are disputed. Several claims have passed through peer-reviewed publication, while important criticisms and responses appeared in 2026 as preprints that remain part of an active argument. No scientific consensus says the plates contain alien spacecraft, non-human probes, or confirmed artificial objects from before Sputnik. That does not make the subject worthless. It means the words evidence, strongest, and aliens need to be separated. Evidence is any observation that changes how seriously we consider an explanation. Strong evidence changes that judgment substantially and survives competing explanations. Proof is stronger still. It leaves the alternatives with very little room. The Palomar transients qualify as observations. Whether they qualify as strong evidence of aliens depends on which part of the argument we examine. Start with what makes the case interesting. The photographic survey existed before the first confirmed artificial satellite entered orbit. The plates preserve physical records from that period. Some point-like sources appear in one exposure and are absent from images taken shortly before, shortly afterwards, or in much deeper modern surveys. Several candidates occur in groups. The April 12th, 1950 plate contains 9 disputed point-like detections in one limited region. A July 1952 case contains 3 bright points that were absent from another exposure taken within about 50 minutes. The researchers have argued that short reflections from moving objects could produce compact points, because the flashes would be heavily diluted during the long photographic exposure. That is more interesting than an unsupported eyewitness story. The plates can be inspected, coordinates can be measured. Source profiles can be compared, statistical methods can be criticized and repeated. Researchers do not have to rely entirely on a person remembering an unusual light many decades later. The dates also remove the most common modern explanation. A brief orbital glint photographed today is probably produced by a satellite or debris. A similar event in 1950 cannot be assigned to the ordinary satellite population because that population did not yet exist. That gives the Palomar observations genuine scientific value. A pre-Sputnik optical flash deserves more attention than an identical modern flash. The Earth shadow result adds another potentially meaningful feature. The VASCO team reported fewer candidates within the calculated shadow at geosynchronous distance than expected from its plate-based simulation. If the result survives improved analysis, it would suggest that direct sunlight was necessary for part of the population. Photographic defects should not respond physically to whether a proposed object is illuminated. The later correlations with nuclear test dates and historical UFO report totals add further interest, although those effects are small, noisy, and disputed. The peer-reviewed 2025 study described them as preliminary associations and did not claim that causation or extraterrestrial technology had been established. Placed together, these features form a coherent suggestion. Brief points appear before known satellites. Some occur in groups or alignments. Their profiles may be compatible with short flashes. Their population may decline inside Earth's shadow. Their frequency may increase slightly around nuclear tests and UFO reports. A reflective object near Earth could connect those observations. The case becomes much weaker when the missing measurements are listed. No candidate has a directly measured distance. No plate provides useful parallax from two observatories. No object was tracked through several positions. No spectrum identifies its material. No radar return has been linked to a specific point. No recovered fragment exists. No repeated signal was received. No clear image shows a constructed shape. No trajectory connects a Palomar source with a reported UFO or nuclear site. No independent observatory has yet confirmed the same flash on an original exposure made at the same time. The evidence consists mainly of presence, absence, shape, date, and statistical distribution. Those properties can suggest an object. They cannot identify its maker. Distance is especially important. An apparently small point could be a weak nearby flash, a stronger reflection far away, a stellar event, or a defect in the photographic material. Without parallax or motion, the proposed geosynchronous location comes from interpreting the shadow pattern rather than measuring an individual object. Once the distance is assumed, the object can be described as orbital. Once it is described as orbital, pre-Sputnik timing makes it appear artificial. Once human satellites are excluded, the interpretation moves towards non-human technology. Each step depends on the previous one. When the first step is uncertain, the final conclusion can sound much stronger than the observation actually supports. The condition of the photographic evidence remains the largest weakness. Hambly and Blair physically inspected Palomar glass copies and found that the disputed points were present on the copies, ruling out a simple one-scanner error. They also identified emulsion blemishes and proposed that holes introduced during the photographic copying process could produce star-like false detections. Their classifier judged the 9 famous marks likely to be spurious rather than ordinary stellar sources. Villarroel and colleagues replied that sub-second flashes should be sharper and rounder than stars exposed for nearly an hour, making the profiles consistent with real flashes. Neither interpretation has obtained decisive experimental confirmation. The exact damaged intermediate plate responsible for every mark has not been produced. A controlled historical emulsion experiment has not established that the Palomar profiles uniquely match short glints. The same sharpness remains compatible with 2 very different processes. This prevents the marks from becoming clean physical evidence. A second weakness is sample definition. Different papers have used different candidate sets. ranging from a few carefully discussed groups to catalogues containing thousands or more than 100,000 unmatched features. A broad dataset improves statistical power, but includes more uncertain entries. A heavily filtered dataset appears cleaner, but may remove the population under investigation. The 2026 critical study argued that the broad samples contain known stars, scanning artifacts, plate defects, geometric patterns, and concentrations near plate edges. It did not reproduce the shadow deficit using the most vetted available sample, and concluded that none of the features had yet been demonstrated to represent genuine optical transients. The response from Villarroel and collaborators argued that the smaller sample was unsuitable for the ensemble tests, lacked complete temporal information, and may have contained plate assignment errors. They maintained that the original findings remained valid. This is not a disagreement over one decimal place. It is a disagreement over which data are valid enough to analyse. Until that issue is resolved, the reported significance values cannot carry the entire argument. A 7 sigma result from a poorly understood sample may be less persuasive than a 3 sigma result from independently verified events. Statistical certainty within a model is not the same as certainty that the model describes reality. The nuclear test and UFO results need even greater caution. The reported associations are small. UFO reports occurred on almost 90% of the dates in the dataset, making a simple present or absent comparison weak. The correlation between daily UFO totals and transient totals was positive, but only 0.138. The nuclear association compared uneven calendar day data across a period in which telescope activity, weapons testing, military operations, and public UFO attention all changed. A weak correlation may point towards a genuine effect. It may also arise from uncontrolled variables. The study's authors recognized substantial noise and described their interpretations as speculative. Critics later argued that Palomar's observing schedule explained much of the nuclear relationship. The original team disputed the method used to reach that conclusion. The appropriate verdict is not that the correlation proves a response to nuclear weapons. It is that the correlation deserves a cleaner test. The phrase "strongest evidence yet" can still be defended in a much narrower sense. This may be one of the more systematic attempts to search pre-satellite astronomical records for a population of short optical flashes that might behave like reflections near Earth. It combines archival imaging, modern catalogues, geometric modelling, and statistical comparisons. Unlike many alien claims, it produces data that other researchers can reanalyze. That is valuable. It does not make the extraterrestrial explanation the strongest explanation. Those are different statements. The evidence may be unusually interesting within the small category of possible pre-Sputnik orbital anomalies. It is not stronger than the standards normally required to discover an astronomical object, identify a spacecraft, or demonstrate extraterrestrial technology. Astronomers regularly demand repeated observations before confirming much less dramatic discoveries. A new asteroid is observed at several positions so its orbit can be calculated. An exoplanet signal is checked across multiple transits and independent instruments. A transient receives follow-up imaging and spectroscopy. A gravitational wave event must match detectors at separate locations. The Palomar points cannot meet those standards after the fact, because their discovery came decades after the exposures. This does not make the researchers careless, it makes the archive limited. The plates may contain the only surviving record of whatever happened. They cannot supply information they were never designed to collect. A useful way to judge the claim is to compare 4 possible conclusions. The weakest conclusion is that the Palomar material contains unidentified marks. That is clearly true. The next conclusion is that some marks represent genuine short-lived light sources in the sky. That is plausible, but not established for the complete sample. The third conclusion is that a portion came from reflective objects near Earth before Sputnik. The Earth shadow deficit and glint interpretation provide a possible case, but distance, sample purity, and survey bias remain unresolved. The strongest conclusion is that those objects were non-human technology. The current evidence does not justify that step. Even when reflective near-Earth objects were confirmed, several possibilities would remain. Balloons, classified human hardware, natural debris, charged dust, unusual atmospheric processes, and unrecognized photographic effects would need to be tested. An unexplained artificial-looking reflection is not automatically alien. The proper scientific conclusion is therefore less exciting than the title, and more interesting than a dismissal. The Palomar observations are intriguing anomalies. They have produced testable claims. They are not proof of extraterrestrial spacecraft. They may eventually reveal an overlooked photographic process, a weakness in historical catalogue construction, a natural population of brief flashes, undocumented human activity, or something genuinely unexpected. At present, nobody can say which outcome will survive. A stronger investigation would begin with the original negatives. Each disputed point should be checked on the first-generation Palomar material, rather than only on later glass copies. Microscopy could reveal whether the emulsion contains a physical hole, chemical disruption, particle track, or pattern inconsistent with light exposure. The same coordinates and times should be searched in original plates from other observatories. Even one independent match would change the case substantially. The full catalogue should be rebuilt through a blinded process. Researchers choosing filters should not know which settings strengthen the shadow or nuclear results. The selection rules should be fixed before the final statistical comparison. Every plate should carry an exposure opportunity record. The analysis should include observation duration, sky area, limiting magnitude, weather, moon brightness, field position, plate quality, copying generation, and scanner. Tests should be repeated after removing edges, extreme plates, crowded fields, and every individual observing year. The shadow search should scan a range of altitudes without selecting the preferred distance afterwards. A real population should produce a consistent physical curve as the assumed distance changes. Modern observations could then attempt to reproduce the effect. Several telescopes separated by known distances could watch the same region near Earth's shadow. High-speed cameras would preserve each flash rather than average it across 50 minutes. Parallax would provide distance. Polarization could reveal reflection. Spectroscopy might identify material. Repeated flashes could measure rotation. Radar and current satellite catalogues could remove known human objects. A source remaining after those checks would be far more persuasive than any isolated historical mark. When such an object were detected repeatedly before entering Earth's shadow, disappeared while shadowed, returned afterwards, showed a controlled trajectory, and could not be found in any human catalogue, scientists would have something approaching strong evidence of unknown technology. When it also transmitted an organised signal, changed course deliberately, or displayed material and behaviour beyond human capability, the alien hypothesis would become much more serious. We are not at that point. What we have is an old survey performing a job it was never intended to perform. Astronomers photographed stars and galaxies. Decades later, other researchers noticed brief sources that did not fit easily into the modern sky. Statistical patterns made the marks harder to ignore, while defects and data bias made them harder to trust. That tension is the real reason the case remains compelling. The observations are not empty enough to dismiss casually. They are not clean enough to support the title literally. Scientists do not yet have our strongest evidence that aliens were orbiting Earth before Sputnik. They may have one of the strongest reasons to investigate a neglected category of historical optical events more carefully. That is a smaller claim, but it still matters. Unexpected discoveries often begin with an irritating result that refuses to fit. Most such results eventually become dust, calibration errors, software problems, or misunderstood natural processes. A few survive. The task is not to decide in advance which kind this will be. It is to preserve the evidence, improve the tests, and allow competing explanations to fail honestly. So after all the old plates, brief flashes, shadow calculations, nuclear dates, UFO reports, balloons, scratches, and statistical disagreements, where does that leave us tonight? It leaves us with 1950s photographs containing marks whose origins are still debated. It leaves us with a research team arguing that some behave like reflected sunlight. It leaves us with critics showing that plate defects and data selection can imitate much of the same evidence. It leaves us without a confirmed object, but with a clear list of observations that could settle the question. Perhaps that is the most useful outcome for now. Not a declaration that visitors were watching Earth before the space age, and not an assurance that every unusual point is merely dirt. Just a difficult data set that has not earned a dramatic conclusion yet. As you settle back, you might think about the night sky above your own part of the world. Today, many moving lights can be identified within seconds. Satellites follow predicted paths. Aircraft appear on tracking applications. Planets can be checked against a map. Even with all that information, an occasional point still appears, brightens, and vanishes before we decide what it was. Most have ordinary explanations. The interesting part is learning how to tell. Thank you for spending this long investigation with Science for Sleep. Tell us where you're listening from, and whether you think the Palomar lights were plate defects, secret human technology, a natural near-Earth phenomenon, or something not yet considered. When you found the discussion calming, you can like the video and subscribe. It helps this quiet science channel reach other people who enjoy difficult questions without rushed answers. For now, the plates remain in their archives. The disputed points remain fixed on the glass. Researchers continue comparing explanations, and the sky continues producing far more light than any one survey can fully understand. Rest well, and let the evidence remain unfinished until better evidence arrives.